Welcome to today's video on zombies and reinforcement learning. So today we're going to be doing something pretty cool. We're going to build a full custom zombie shooter game in Pygame. It's going to have 3 levels. It's going to be a 2-dimensional game where you can roam around different environments and shoot at zombies, and of course the zombies are trying to get your player. We're then going to take that game and convert it into a custom OpenAI gym environment. So if you're not familiar with gym is basically an AI-ready set of environments, or it's a way that OpenAI published to make a set of environments AI compatible so that we can train reinforcement learning agents on them. So we're going to code the full game from scratch. We're going to make it human playable. We're going to add sounds and graphics and all the fun stuff. And then we're going to turn around and turn it into a gym environment. Once it's a gym environment, and we're going to code through this step by step, the whole thing. Once it's a gym environment, we're going to turn around and train a Q-learning algorithm on how to play the game. So we're going to build a full-fledged AI that's capable of taking images from the game, processing them, understanding what to do, and then taking action and playing successfully, and in some cases beating the game. I'm going to go ahead and show you what the end results are going to be before we go any further. I'm going to run my test.py here. So here we have our AI playing the game, and you can tell it's a little energetic, we'll call it. But it is fairly successful. It's able to identify the zombies. It's able to roam around and shoot at them. And we are able to advance through the levels. And you can see that the levels change a little bit as we go. The zombies also get faster as we go up the levels, and there are more of them. So just like any other video game, it's going to get increasingly more challenging, and we're going to train the AI to play all 3 levels. This is a fairly resource-intensive project. The standard buffer size I have takes about 16 gigs of memory. You do probably want a fairly high-end computer with a GPU in order to train this in any reasonable amount of time. Even with that, this can still take 20, 30 hours to train successfully to the point where I have it right now. So this is not something, if you're hanging out on a Chromebook, you are probably not going to be able to do this unless you rely on some kind of GPU hosting. I have other videos on that. I'm going to make the assumption that you're on Linux. You can probably do most of what I'm doing here in Windows. I don't think that'll be a problem, but I am on Linux, so that's what we're going to be using in this course. I am also going to be using VS Code and a Anaconda environment. In the video description, you will find a starter project that has the images, sound files, and other media that are necessary to code the game. You will be writing all of the code by hand from scratch over the course of the video, so the code itself is not present in the starter project. Finally, this is not a fresh series. I released this originally as a series of individual videos, and what I found is that most people on YouTube don't really love the long video series. By the time, when I posted the first one, by the time I posted the second, people weren't interested anymore, and it never really took off. I think some of them landed with 30 or 40 views. I put a ton of time into this series. It's 6 hours long. So I decided to put it all together as one big video, since that seems to be everyone's preferred format, and I am re-releasing. I am leaving most of the transitional information and language in there because I did have some valuable tidbits as we went from video to video, but you will hear me throughout the video series here, saying things like, end of video 5, and, we're starting video 6. Just don't be surprised. Like I said, I am combining a previous video series into one big video for your enjoyment. I'd love for you to drop me a comment and let me know if that's, do you like long strings of videos? Do you prefer having one big multi-hour video that's the entire course? It seems like more people watch the full-length videos, but I'd love to hear what you all think. Finally, in addition to the starter project link, you will also find a link to Discord in the video description. I'd welcome you to come join the Discord. We talk about AI, robotics, autonomous gameplay, all the fun stuff. If you need any help with this series, you're welcome to post a comment or come hop on Discord and talk about it there. And then finally, I will post a link to another video I have on using Runpod to train AI models remotely. If you do not have a machine that you can use to train this, I would highly recommend checking out Runpod or another service like it and using that to do your model training. That way you can use a low-end GPU or a low-end computer without a GPU and still manage to train some of these models from anywhere. So with that, I will go ahead and end the introduction here. We're going to kick off in just a moment and go ahead and start building this project. I hope you enjoy watching it and building it with me as much as I enjoyed making it. Welcome to the first video in this series on zombies and reinforcement learning. So let's talk through some of the assumptions I'm making and sort of the things I'm using. So I'm going to be on Linux. I don't think there's anything about this that wouldn't work on Windows, but I do just want to start out there. I'm on Linux. You may see differences on Windows. I am going to be using VS Code. You do not have to. You can use whatever editor you're comfortable with, but you'll see me primarily working in VS Code throughout the course here. I'm going to be using Anaconda for managing my Python environment. So I think quite a few people are going to be using that. If you're not, I would recommend creating a virtual environment in whatever tools you're comfortable with. And then we are going to be using Python 3.11. So that's one part that is important. If you're using a later version of Python or an earlier version of Python, this may not work quite the same way for you. So I would make sure that whatever tools you're using to create your virtual env, you are creating Python 3.11. Finally, there is a starter project that's going to be out there. And that starter project will have this set of files. So it's going to have the images used in the game. It's going to have the sounds used in the game. It will have a walls.py, just because I didn't want to make you write all of these, coordinates for the walls. That sounds awful. And then it's going to have the requirements.txt. So that link will be down in the video description. You should go ahead and grab it and pull that down as your starter. So let's go ahead and we're just going to do a conda create -- name. Again, assuming you're using Anaconda. And I am going to call this zombie shooter YouTube. You can call this whatever you'd like. Just, actually I'll do zombie shooter v1. And you'll notice I've got Python equals 3.11. We're just gonna say yes. All right, I'm gonna go over to my tab where I've got the zombie shooter starter project downloaded. And I'm going to go ahead and do conda activate zombie shooter v1. And then we're going to do a pip install -r requirements.txt. And a note on this requirements.txt. So I've got this extra index URL in here to pull down CUDA. If you need a different version of CUDA for your GPU, or you don't have a GPU, this may need to change for you. This works very, very well with the 30 series on my Linux install, but you may need to tweak this. Something I would recommend is going to NVIDIA's Torch installation instructions, and they're going to have a way to get the CUDA install that is appropriate for your system. All right, so this will take just a moment. I'm going to hit pause while this runs. All right, and that looks like it's finished. So let's go ahead and fire up an IDE here, code dot, and that's going to get us our VS Code. All right, so we've got VS Code. Let's just kind of start by stubbing out the project. We've got our walls.py already. We're going to create a bullet.py. We're going to create a game.py that kind of holds the game itself and the main game loop. We're going to create a main.py. And we're going to do a characters.py. And then we are also going to create a util.py. All right, and our strategy here, again, is going to be to build a complete human playable game with minimal concessions for AI, and then kind of strip that down and turn it into an AI playable thing. There will be some code duplication. There will be some effort duplication. If I just sat down with the final project and we coded through that, you would have less total code to write. But the whole point of this series is to show you how to take a game and turn it into something that an AI can play, an OpenAI compatible gym environment. So I don't want to skip any steps. I want to start with something that's more or less not set up for gym. Again, some small concessions. We'll have a step method. It just won't do what you'd expect it to do for gym. And then, we're going to take that and convert it. So let's go ahead, and I am going to just get a game class out there. So in game, we're just going to say class zombie shooter. And for now, we'll pass. We're not going to do anything with it. I'm going to come over here to main.py. Let's see. And we're just going to go ahead and do some of our imports. So from game import zombie shooter. And then we're going to set some of our variables here. So window width, window height, no, I could spell height, equals 1200, 800. And then we'll do world width, world height equals 1800, 1200. And what that is you'll notice that we kind of pan around the world a little bit in the game. This is setting the overall size of the world that we're playing in, and then the world and window height. So we'll do FPS, FPS equals 60. Okay. Now let's come over here to our game, and we're going to add some of the parameters that we need. So we're going to do window width, window, let's see, height, world height, basically all the things we just started out with. World width, FPS, and we're going to start out with sound equals false. So we've got a sound variable. So let's go ahead and come back over here to, let's just do print zombies. We'll pull in import time, and we're going to say time dot sleep. Actually, we don't even need to do time dot sleep because this isn't a loop yet. We'll get there. Okay, we're just going to start out the class, and in the class definition, self, we'll come back over here and print zombies. All right. And I am being dumb here. This all needs to be in the init method. Sometimes when you're rewriting code you've already written, it's easy to turn your brain off for a minute, which is what just happened there. All right, so now we have our zombie suit shooter class with our init method with our print zombies. Now I can come back over here to main.py, and in main.py we are going to say game equals zombie shooter, window width equals window width, window height equals window height. Go down to the next line. World height equals world height. And world width equals world width. And then FPS equals FPS. All right. And for our human playable one, we're going to say sound equals true. This doesn't do anything yet, but it will later. And then we're going to have in our game a step method. This is probably the one concession to the fact that this will be AI eventually that we're going to go ahead and code in here, is we're just going to have a step method that takes self and print playing zombies time.sleep 1. All right. So when I first coded this out, I coded out the main loop of the game in main.py, just to kind of stub it all out and make it work. When I started down the path of putting this in, in something that was a little bit more supportable, something that we could turn into an AI experience here. I moved it to the game class. And implemented this step method so that we could call it externally. So that's what we've got here. So we're just going to say this is going to be our game loop. And basically your game loop is you're going to just run it in a while true continuous loop. Hey, we're going to run game.step. We don't have to worry about timing. Pygame is going to take care of that, or some of the things we're going to do in Pygame. So let's go ahead and run this. Hey, and we get our continuous where we kick off our zombies and then we are playing zombies. All right, so that is actually, we'll come in and add, actually I don't even think we have to add other imports later. This is the entire main.py. This is all it's ever going to be while we're working on our human playable version of this. So we can now come in here and start working on our game.py. So let's start with all of our imports because there are a few. Oh, and I also just realized I need to set select interpreter, zombie shooter v1. Let's go ahead and import Pygame, import sys. We bullets, actually we've already got our classes, so I'm just going to say from bullet import star, from characters import star. There are no imports there yet, but or there are no classes to import, but we'll get there. So from util import star, and from walls import star. And we'll be a little bit more specific about this as we get into it. But for now, that gets all of our imports. So let's go ahead down in our init method, and let me just delete these. And we're going to go ahead and start to declare the variables that we need. So self.window width equals window width. Oh, again, I'm in the step method. So self.window width equals window width. Let's give ourselves a little bit of space here. Self.window height equals window height. Self.world height equals world height. Self.world width equals world width. All right. Some other variables we want self.treasure chest. We'll be including those much later. Equals none. Self.health drop equals none. Self.paused equals false. And then we will say so there are two gun types in the game. There's a single fire and a shotgun. We're going to start with self.gun type equals single. Self.fire mode equals single. All right, and now we get into the Pygame parts. So let's go ahead and do Pygame.init self.screen. This is important. The screen is the object managing the screen for the rest of the time that you're working with this. So we're going to do self.screen equals Pygame display.set mode, and then double parentheses. That's important. And we're going to do window width and window height. All right. We're going to do Pygame.display.set caption. Zombie shooter is what we're going to call our game. Self.font equals Pygame.font.sysfont. None and 36. Self.clock. This is how Pygame keeps track of the game speed. Pygame.time.clock and self.fps equals FPS. All right, and then we're going to set walls at the beginning to self.walls equals walls1. So let's talk about that for a moment. In our walls.py here, we're basically going to increase the complexity of the map as we go through the levels. So at the beginning, I want a couple of walls just so the player can get used to the idea that walls are a thing. And the walls are going to be green. I really meant for them to look kind of like hedges. So we're going to have a couple of walls. As we go into the second round of the game, we get different walls. As we go into the third level, we get, again, different walls. So, but to start out with, we're just going to start with walls 1. All right. We don't have a player yet, so I'm just going to say to do define player. We're going to set self.background color equals 181, 101, 29. Self.wall color. That should give us a nice orangey background color. 250.32. Self.border color equals 255.0.0. Self.announcement font. I know this part is a little bit of a grind. We're just getting through all of the initial variable declarations. Pygame.font.sysfont. Oh, an equal sign would be nice there. This is also probably a good time to say this is not going to be a short series. This is, you can probably tell from the number of files just in sort of round one here. We're going to be writing a lot of code. I should have kicked things off with that. If you are not here to spend a few hours while you're building this out, this is not just the first video, 30 minutes, and then we're done. So just know that as we get into it. Self.bullets. We'll need a place to store our bullets. Self.zombies. We need a place to store our zombies. And then we're going to get into things like our zombie top speed. And all these things are variables because we want to change them with the levels. So self.zombie top speed equals 1. Self.level goal. In other words, how many do we have to get to go to the next level? We're going to say 5. Self.max zombie count equals 5. Self.level, we're going to start with 1. And self.sound equals sound. Okay. Now, let's go take a look at our step method. Actually, let's go ahead and run it. Let's see what happens. If we get any crashes, if we get any errors, we're just going to come over here and run main.py. And you notice we get this kind of blank page. Not a whole lot here because we haven't done anything. We set a bunch of variables, but we didn't actually do anything with them. And we're just going to go ahead and kill that. So that is just fine. Let's go ahead and set up our next method, which is going to be it's going to be fill background. And then after the fill background method, that'll probably be a really good stopping point ahead of the next video. So we're going to say self.screen.fill. Self.background color. We're going to say score surface. We're going to keep track of our score. Is self.font.render. Score and self.player. We don't have a player object yet, so we can't do that. Never mind. That's okay. So we can't do score surface. We can't do health surface. We can go ahead and set up our level surface. Self.font.render. Level, just to give you an idea of what'll be here. Self.level. And then we will set true and 0, 0, 0. Self.screen.blit. It's going to kind of post it to the screen. We'll do level surface 10, 60. All right, and that's going to be a position. And then let's see. I think that's probably most of what we can do here. Let's go ahead and throw in a to-do. So to-do, set player stats, and then another to do set ammo message and gun type. All right, let's see. Oh, and then we should definitely call self.fill background down here and make sure that it actually works. Oh, and we are not working. Let me look at why. Because we should at least be getting, oh, well, you know what? We haven't done anything to tell it that that color is different yet. We've got our wall color, we've got our background. Well, we did say self.screen.fill background color. Okay, this should be at least doing our background color. Let me take a look at this for a moment. All right, and I think I see what we're missing. We need pygame.display.flip. Updates display. And if you're wondering why we don't just put it in fill background, so fill background is going to be every single time we loop, we're going to fill the background with the background colors, and then we're going to put the walls on it, and then we're going to put the players and the zombies on it, and then pygame.display.flip is what at the very end of the loop is going to actually do something. And you can see here we now have our nice background of zombie orange with a level 1 displayed. Eventually that'll be, gun types and number of bullets and lives and all that fun stuff. But for now, it's just level 1 with a background. All right, I am going to go ahead and end this here. In the next video, we'll probably start coding out a little bit more of our main loop, and we might start playing with the player class or zombie class. All right, I'll see you in the next video. Welcome to part 2 of Zombies and Reinforcement Learning. In this video, we're going to go ahead and start working on our characters, our player and our zombies. So let's go ahead. We're going to need random. We're going to need Pygame. We're going to need math, not map, math. And we're going to say from util import star, and we don't have util yet. In fact, let's go ahead and code out util. We're going to need that in this one, so let's just put it together. So these were just kind of general get and check collision methods. In Pygame, you're not going to, it's not like there's anything in the game engine, at least nothing I've seen, that naturally recognizes that what you're putting together is an object that shouldn't be run into. It's going to help you throw your graphics on the screen, but it doesn't care if they, flow into each other. So we need a way to check for collisions. That's checking for collisions if your player is running into walls. That's checking for collisions if you have a bullet hit a zombie or a zombie hit the player, or lots of reasons to need to do a collision check. So we're just going to check collision, rect and rect list. Everything in here is a rectangle. For I in rect list, if rect dot collide rect I, then return true. Otherwise, return false if none of them hit. And then here, we're going to go down to the bottom, and we're just going to copy paste that. Copy paste our check collision. And in this scenario, we're not trying to return whether or not something collided. We're just returning, we're going to do get collision. So we want to return the actual collision here. So we're going to return none if nothing fits. And then I'll just remove one of those extra lines. All right, so we now have a check collision and a get collision. And we'll frequently use those two together. We will use this to see if there are any collisions, and then we'll immediately use this if we need to get the actual value to pull back what that collision was. All right, so we've got that. Now here on back under character Py, we're going to define a class player and an init method that includes self. It's going to include world width, world height, and walls. And then we'll go ahead and start declaring some of our player variables. So we'll need self.size equals 50. We're going to say our player is 50 pixels wide. Self.speed is equal to 5. The self.rect, which is where is our player. Self.x equals world height divided by 2. Self.y equals world, and actually, hang on, this one should have been self.width and self_height divided by 2. All right, so what this is doing is this is basically saying that self.x, self.y, the x-y coordinates, so our player, are going to be right in the middle of the screen. You could put the player anywhere, as long as it's somewhere in the world dimensions, but we're just going to say right in the middle. And then we're going to say while true, self.rect. And this is a bit of code I wrote because I was having trouble with the player appearing, in a wall or on a wall. So I'm basically saying Pygame.rect self.x, self.y, self.size, self.size. By the way, this is your starting x position, your starting y position, and then this is defining, a square that the player is sitting in, which is why you've got self.size twice. We're going to do if check collision self.rect with walls. So we do need walls in order to define our player. Self.x plus equals random.randint -5, 5. And I will do the same with self.y. Else break. So what we're basically saying here is sit here in loop and give the player a starting position in the middle of the screen and then wobble that starting position until you find a spot with no walls. And that was an easy way for me to not have to worry as much about the player landing on a wall as I moved the walls around and played with things. So we're also going to go ahead and say self.score is equal to 0. We have no score starting out. Self.ammo is equal to 10. Self.health is equal to 5. Self.images, that's going to be a dictionary. And then we will go ahead and pull our images in. So for direction in up, down, left, right, image equals pygame.image.load images/player self.direction.png. And then we're going to say self.images direction equals pygame.transform.scale image self.size self.size. And then finally self.direction equals up to start with. So let's talk about what we just did here. Obviously we placed our player in the world. This is basically going to start with our list of directions here. It's going to loop through and it's going to create a dictionary of images where you can pass in up, down, left, right, and get back an actual image object that is, a Pygame image object scaled to the size that we put up here for our player, a 50 by 50 image. You'll notice in the images folder here, if you go into player up or player right, you've got your player here that is going to be, facing whatever direction. She's a fairly large image, or shows up that way in VS Code, not actually all that large. But yeah, so we're basically going to pull in, player up, player right, player left, so that we can display those views on the screen. And then we also have our zombie right, left, up, down images. And if you're curious, these are all AI generated. I am not capable of artwork. If this is the kind of thing you find fun, then you could put together your own completely custom images for zombies pointing left, right, up, and down, and your player pointing whichever direction you want her pointed. All right, let's go back to our characters py. Now we need a draw method. I wanted the players, or I wanted the different characters to understand how to draw themselves. So we're going to say draw self screen camera X camera Y screen.blit self.images self.direction, and then we're going to say self.x minus camera X, self.y minus camera Y, and that is done for that one. All right, let's go look at our zombie now. So we're going to say class zombie, def init as always, and that's going to be self, world width, world height, size equals 50, speed equals 1. Okay. And let's see if there's anything we can, not enough we can copy. All right, we're going to say self.size equals size, self.world width equals world width, self.world height equals world height, self.speed equals speed. That changes as the levels go on, of course. Self.x, self.y equals self.spawn, because we want our zombies to be able to spawn in various portions of the map, although they'll always be around the edges. We'll do something very similar to what we did here. So I'm going to go ahead and grab the next few lines here. And then instead of player, we're going to say zombie. but otherwise these are the same. We've got a self.images, we've got a for direction, and we're going to grab, you know, our directions. And then we will also go ahead and say self.direction out of the box is going to be up. And then self.rect equals Pygame.rect 0, 0. Self.size, self.size. And then we'll say self.rect.center equals self.x, self.y. Okay. Now we need a spawn method to say where our zombie is going to spawn. So we're going to say def spawn is self. Spawn positions equals, we'll do, and this is, we're going to have a whole bunch of randomness here. So we're going to say random.randint 0 self.worldWidth minus self.size 0. So that's our top edge. And then we're going to have random.randint 0 self.worldWidth minus self.size self.worldHeight minus self.size. Okay. Bottom edge. And then we're going to say 0 random.randint 0 self.worldHeight minus self.size. And we're basically defining the edges of the environment. And then self.worldWidth minus self.size random.randint 0 self.worldHeight minus self.size. Okay. And then we're just going to return random. So we've basically created, you know, a matrix of positions around the edges. And then we're just going to return random.choice spawn positions. So every time a zombie spawns, we're going to pick a random position from one of the edges of the map, and we're going to spawn the zombie from that location. That is our target here. That's what we're doing. So let's go ahead and code our, we get to some of the, well, let's do our draw method. We'll need that. So, and then really our draw method can be, let's see, do we even need to change anything? I don't think we do. I think the draw method is going to be identical to what it was with our player. All right, now we need to actually build in some basic intelligence for our zombies. We're not going to make our zombies AI driven. The player is going to be AI driven. The zombies will follow just some basic movement logic. So we're going to call it move towards player. So def, and if you think about it in zombie movie terms, they're never very smart, right? Your zombies are just running after the humans in the scenario. So that's what we're doing here. So we're going to say move toward player, self, player X, player Y, and walls. Okay. So we're going to say dx dy is going to be player X minus self.x, player Y minus self.y. So that's giving us the distance between the zombie's position and the player's position. The zombies have an advantage here. They always know where the player is. We're going to do distance equals math dot hypotenuse dx dy. If distance is not equal to 0, then we're going to do some normalization. dy equals dx divided by distance, dy divided by distance. Okay. And then we're going to try a couple of different methods of movement. So we're going to try horizontal movement first. So we're going to say new x equals self.x plus dx times self.speed. New rect equals Pygame dot rect. New x self.y self.size self.size. Can move x equals not check collision new rect walls. So let's talk about what we're doing here. So we are attempting to move our zombie along the x-axis towards the player. We're declaring a new rectangle that's in the new position. We're declaring it to move to the new x with the existing y and the current size. We're then validating that that's an okay move. So we've kind of created a temporary, and you'll see this used in other places in this code. We're creating a temporary new rectangle for the new position. We're moving it towards the player, and then or moving it towards whatever the objective is. And then we're going to see if that was valid, and if so, then we set it to the new position. So we're going to go ahead and say if can move x self.x equals new x, else we're going to go ahead and do new y equals self.y plus dx or dy times self.speed, and then we're actually going to multiply it by 1.5, and what we're trying to do here is increase speed along y-axis if horizontal movement is blocked. So why are we doing that? This was one I just kind of found through experimentation. If I just used a basic, move towards player X, move towards player Y type of logic and did not include this, then zombies would stop at a wall. They would basically run into a wall and then move incredibly slowly towards the player. They would still get there. They would just have a really hard time creeping along the wall. So this is an attempt to say, hey, if you hit a wall, be a little bit more aggressive in that y-axis movement until you get free, basically. So here we're going to say new rect equals Pygame dot rect self.x new y self.size self.size. Okay. If not check collision new rect walls. Then we're going to go ahead and do self.y equals new y. All right. Finally, we're going to say new y equals self.y plus dy times self.speed. Oh, that needs to come in one. Okay, we're going to say try vertical movement next. And same kind of deal here. So we're going to say new y equals self.y plus dy. Oh, we already did that. Sorry. We're going to say new rect equals Pygame dot rect self.x new y self.size self.size. We're going to do the same kind of logic. Can move y equals not check collision new rect walls. And then we're going to say if can move y self.y equals new y else. And now we're going to increase speed along x axis if the vertical movement is blocked. So same kind of logic. In a world with no walls, this logic would not be necessary. This is because we, again, needed the zombies to be able to climb over walls when they needed to, or get around walls more quickly. Self.x plus dx times self.speed times 1.5. New rect equals Pygame dot rect new x self.y self.size self.size. Okay. If not, check collision new rect walls, then self.x equals new x. Okay. We will go ahead and update position and direction. So we'll go ahead and say self.rect.top left equals self.x self.y. And then we will go ahead and set the zombie's direction based on movement. So we didn't have to do this for the player because the player's direction is going to be easy. You'll have some kind of input. You're going to say go left, and then the direction will move. The zombie, we're defining this programmatically. We're defining a new direction based on the player's location. So we need to actually show which way it's going. Otherwise, you just end up with a static zombie image. If ABS dx greater than ABS dy, so we're basically saying what was the larger motion. We'll say if dx is greater than 0, then self.direction equals right, else self.direction equals left. And then we'll throw an else in here for if dy is greater than 0, then self.direction equals down, else self.direction equals up. All right, and then assuming no typos, we are done with our zombie class and our player class. I think that's a really good place to just go ahead and stop the video. You've got your zombie, you've got your player. In the next video, we will come back over to the main loop and start to integrate some of these components. Again, there's a lot more code to write, but we're making great progress here. So see you in the next video. All right, welcome to part 3 of Zombies and Reinforcement Learning. In this video, we're going to go ahead and start to code out the main loop here a little bit more, and hopefully you will get to see your player moving and maybe even some zombies moving. Let's just see how far we get. So actually, before I go any further, let me go ahead and check everything we're doing into Git. new file, .getignore. Always a good idea to go ahead and get your getignore out there. Right now, that's going to be with PyCache. So now if I run a git status, I no longer see it. Video 2. That's the last thing we did. All right. That way we can, if I make a mistake, I can always go back. All right, in our step here, so the first thing we're going to need to do is start to capture some Pygame events. So Pygame events are going to be things like key down, mouse click. This is us interacting with the game. So I'm going to say for event in pygame.event.get if event.type equals pygame.quit. Then we'll go ahead and do a pygame.quit and sys.exit. Okay. Elif event.type is pygame.keydown. If event.key is Pygame. So we're capturing certain keys kind of right up front, and then we'll look for other key presses a little bit later. But right now we're going to go ahead and grab key tab. We'll do, and this is our changing gun type. So the tab key is going to change from shotgun to single. So single if self.gunType equals shotgun, else shotgun. So basically, if it's already shotgun, go to single. If it's single, go to shotgun. And funny story on this part, so I actually built the original copy of this game with just single shooter, and no health drops and no loot drops. Posted it out for a few friends. One of them liked the game, thought it was cool, went and pull requested a feature for, for the shotgun and the health drops and the loot drops to pick up more shotgun ammo. So it's cool when someone likes the thing you've built enough to go and contribute to it. So I just want to go ahead and credit that. I'm not going to throw his name out, but this part was an addition. So switched to self.gunType mode. Elif event.key equals pygame.k space if self.gunType is single. Then we're going to do fire. Oh, we don't even have that yet. So I'm just going to say to do fire single bullet. And actually, you know what? Let's just go define. Let's go define the method. We don't have to put anything in it. So let's go fire single bullet. And that will just take self. And for now, we're just going to say pass. Actually, we'll do one better. Print, bam. All right, we're going to be really creative there. We'll make that do something later, and we will put a to-do up here. To-do complete bullet method. And if you're wondering about my use of to-dos here, when you're building a somewhat larger project like this, especially for me, because I'm re-implementing it, on video, it's easy to forget pieces because these projects, it's not like when you're coding something like this out the first time, you actually code it from top to bottom like we're seeing. you build in bits and pieces and you find things that don't work and you find, chunks that you need to add later. And it's much more organic. When we're re-implementing, it's a challenge actually to remember where everything went and not leave pieces out. So I'm throwing to-dos among the code base, so as we go through, if something doesn't work, I can go back and check the to-dos and we can find the pieces that we weren't able to code on the first go around here. So anyway, just a little soapbox there. We're going to do event.key, so we said k space. We're setting, gun type to single, so we're going to do self.fire single bullet. Else we'll need another method here. So this is going to be def fire shotgun bullet and print bam bam. All right. Okay. Oh, and we do need to go and say self, otherwise that is going to error. Okay. And then finally, we're going to say elif event.key is equal to pygame.k escape self.toggle pause. Okay. And I will go ahead and def toggle pause self. And that again to do complete toggle pause method. Okay. So now we should have the ability to pause our game. We'll say if self.paused return. Okay. Another piece that we want to go ahead and get in is our Pygame, the self clock tick. So here we've got time.sleep implemented. We actually don't want to have our, we don't want to have that as our method of maintaining time. At the very end of this, we actually want to say self.clock.tick, and then we're going to say self.fps, and that will manage, how fast the game runs. So let's see, what do we not like? Expected indented block. Do you not like something? Hang on. Our editor is telling us something's wrong. I'd like to understand what it is before we go too much further. For event, those elifs look good. That all looks good. I feel like my indenting is decent. Let's go run it and just see. Yep, def step. Oh, I think we did indent. What don't you like? All right, I'm going to pause and figure out what's wrong here. All right, it should have been obvious. I did not put a pass up in this method. So it wasn't complaining about my step method, it was complaining about it thought toggle pause, was still going because I did not implement that pass. So now this really shouldn't do anything more, but there we go. Now we're back to our screen working. Again, we haven't really added anything extra to it, so no extra functionality. But let's keep going. So back up here, we are going to set player moved equal to false. We'll be using that variable later. We will go ahead and set up our zombie spawn functionality. So we're going to say if the length of self.zombies is less than self.maxZombieCount and random.randint 1 to 100 is less than 3. So we're basically going to say that for any given frame, if we're below our max zombie count, there's a 3% chance of spawning a zombie. So we want some randomness there. So we're going to say self.zombies.append zombie world height equals self.world height, world width equals self.world width, size equals 80. We want our zombies to be a little bigger than our player. And then speed, and I thought this was a fun bit of game mechanics. So speed is not going to be a single set value. It's going to be a random.randint between 1 and self.zombie_top_speed. So what's that going to do? If we just set it to zombie top speed, so right off for level 1, top speed is 1. We're saying, you know, between 1 and 1, obviously the value is going to be 1. As we progress through the levels, that zombie top speed is going to go up. So we'll actually have zombies of various speeds. So you'll have zombies of speed 1, speed 2, and speed 3, all, you know, playing in the same realm, somewhat randomly based on this line. So let's go ahead and we're going to let's see. We're going to go ahead and get our additional key presses here. So we're going to say, and we can actually remove this playing zombies text. We don't need it anymore. That was just to show the function was running earlier. So again, we're going to go ahead and get pygame.key.getPressed. And this will be some of our directional code. So we're going to say new player x equals self.player.x if keys pygame.ka. And by the way, just to take the mystery out of this, what this is saying is it's grabbing Pygame and then it's saying if the key of A was pressed inside the game. So we're just going to use your standard WASD for movement inside this one. So this is going to be left. You could just as easily map this to anything you wanted it to be. But for now, we're going to say new player x minus equals self.player.speed. And we're going to set self.player.direction equals left. If keys pygame.k.d, then we're going to say right. And then new player x plus equals self.player.speed. And self.player.direction equals right. And you'll notice that it's not liking self.player, it's not auto-highlighting it, and I think that's because of one of our to-dos up here that we didn't do. We never defined the player, because when we first started this main loop, we had not yet implemented the player class to be able to go define it. So, so let's go ahead and define our player so that we can start working with them. Self.player equals player. World height equals self.world height. World width equals self.world width. Walls equals self.walls. Okay, so we should now have a player. Let's come back down here to the bottom. And now you'll notice that self.player.speed is lighting up nicely for us. So let's go find, hang on a moment, let me find where I was. Okay, so we now need to define new player rect is equal to pygame.rect new player x self.player.y self.player.size and self.player.size. And you'll notice the same logic here that we were using when we were moving the zombie. We're going to define a new rectangle in one direction, the new player X with the existing player Y. We're going to do a collision check equals check collision. New player rect with self.walls. And then if not collision and self.player.x is not equal to new player x and 0 is less than or equal to new player x less than or equal to self.worldWidth minus self.player.size. We're basically just saying you can't go outside the world. Then self.player.x equals new player x. And we also need a to-do here to play walking sound. We haven't done anything with sounds yet in the series. We'll get to that, once we've got all the basic mechanics down. So, all right, so we've done self new player X, and we now need to do basically the same thing with new player Y. So let's go ahead and say new player Y is equal to self.player.y if keys pygame.kw, so W in our WASD, this is going to be up, then new player Y minus equals self.player speed. You should be used to this logic at this point. Self.player.direction is going to be equal to up, lowercase up, if keys pygame.ks, and we're going to say down, new player Y plus equals self.player speed. You'll notice the first one I'm doing minus equals, the second one I'm doing plus equals because it's different directions. That's, that is an easy mistake to make. Make sure you're paying attention to those signs. So we're going to say self.player.direction equals down. We're going to have our new player rect equals pygame.rect self.player.x new player Y self.player.size and self.player.size again. All right, and then just like before, we're going to go ahead and do our collision is check collision new player rect self.walls, and then also just like before, we are going to say if not collision and self.player.y is not equal to new player Y, and hit my caps lock there, and 0 is less than or equal to new player y is less than or equal to self.worldHeight minus self.player size. Then self.player.y is equal to new player y. And we will add another to do play walking sound. Okay. Now we want to go ahead and say we've got our new player X and our new player Y. So now we can actually set up the real player rectangle here. So we're going to say self.player.rect is equal to pygame.rect, self.player.x, self.player.y, self.player.size, and self.player.size. Okay. We are going to go ahead and set collision equal to false. We'll be using that later. Now we want to update the camera position to focus on the player. So we're going to say camera x equals self.player.x minus self.window width divided by 2. We're going to say camera y is equal to self.player.y minus self.window_height over 2. And then we're just going to make sure that we're keeping the camera inside of the world bounds. So we're going to say camera x equals the max of 0 or camera x self.world width minus self.window width. And camera y is equal to the max of 0 and the minimum of, so the max of 0, that's going to make sure that if it's below 0, 0 is now the max. And then we're taking the minimum of, camera y and the world height minus the window height. So that's going to make sure that we're staying inside of our world here. All right. I am just going to add a big to-do here that says add zombie logic. And we're going to jump down to a lower point in the code. This is where we've got our fill background. And I think we want to go ahead and we're also going to add a to-do here to add bullet logic. We don't even have bullets yet. And then we're going to say self.player.draw, self.screen, camera x, camera y, to do draw zombies. And then let's see. Let's start there and see if I've got enough, if we've got enough code to actually display our player. I think we do. Hey, we have our player. And we are able to move our player around with WASD. Now, it's not super obvious right away that the player's moving once she hits the middle of the screen because there's nothing to reference against. It just, it's a solid orange background. But yeah, so we now have a player on the screen who can move around and interact with the environment in some way. So I think that is probably a really good place to go ahead and end this video. In the next video, we're going to start to put together the bullet logic, so our player can, shoot at things, and then we'll also hopefully start working on the zombies and their logic in the environment. So see you in the next video. Welcome to part 4 of zombies and reinforcement learning. In this video, we're going to go ahead and start working on our bullet class here. Start getting some of that functionality put together. So opening up your bullet.py, and just to recap, in the last video, we got to a point where you had a player. That player was able to move around the environment. You should be able to run your main.py at this point and see this interface with your player on a screen. So if you don't have that working, stop, go back to the last video, figure out what's broken before you come here. So we've got our bullet.py. We're going to go ahead and import Pygame. We will import math. And let's go ahead and get our class single bullet. And we're going to say def init. And we need self x, y, and direction. Those are the things that we need when instantiating a bullet object. So we're going to say self.x equals x, self.y equals y, and self.direction equals direction. And then this isn't strictly necessary, but I think some logging is probably helpful here. So we're just going to do printf bullet launched in direction. And then, as with everything else, everything is a rectangle. Pygame.rect x, y, 10, 10. So we're basically saying that we're starting out with our initial x and y coordinates, and our bullets are going to be 10 pixels wide. We're also going to make them fairly fast compared to other things in the environment. We're going to say our bullet speed is 10, and we're going to make our bullet color equal to 192, 192, 192. Okay. Now we're going to say def move self if self.direction is equal to up, then self.y minus equals self.bullet speed. Elif self.direction equals down. Oh, I forgot my colon there. Self.y plus equals self.bullet speed. Elif self.direction equals left. Self.x minus equals self.bullet speed. Elif self.direction, not elf, self dot direction equals right. Self.x plus equals self.bullet speed. All right, and then self.rect.top left equals self.x, self.y. Okay, give myself a space there just to make that a little cleaner. All right, so that's our move method. Now we want a draw method. And you'll notice that every single time I build something that's drawable, I am building a draw method into it. The intent there is that in the main loop, we can just loop through objects and tell them to draw themselves. We don't have to implement that logic external to the object. We can just say, hey, object.move, object.draw. And it should have the internal logic to handle those actions. So we're going to go ahead and say self screen camera X, camera Y, and pygame.draw.rect screen self.bullet color, and then self.rect self.x minus camera x, self.rect.y minus camera y, and 10 and 10. Okay. Now we're going to do our class shotgun bullet. So class shotgun bullet def init self x y direction angle offset equals 0, self.x equals x, self.y equals y, self.direction equals direction, and self.angle offset equals math.radians angle offset. So we're going to have our shotgun blast go off in a, kind of a triangular direction out from the trail or character. So bullet launched in direction with angle offset. All right, self.rect equals pygame.rect x, y, 10, and 10. Self.bullet speed equals 10. Self.bullet color equals 192, 192, 192, just like before. We're going to say self.dx, self.dy is equal to self.get movement vector direction and self.angle offset. And I know we don't have a get movement vector yet. We'll go ahead and do our def get movement vector. Self direction angle offset. And then we want our direction angles equal to up. So we're going to do math.py divided by 2. Oh, not path, math.py divided by 2. Down will be math.py divided by 2. Left will be math.py divided by 2. And right will be 0. Okay. We're going to get our base angle. Direction dot angles direction. So basically, what's straight? What's the first bullet is what we're looking for here. We're going to say final angle equals base angle plus angle offset. Dx equals math dot cosine of final angle times self dot bullet speed. Dy equals math dot sine of final angle times self dot bullet speed. Return dx dy. Okay, and then finally move is going to be def move self.x plus equals self.dx, self.y plus equals self.dy, self.rect.top left is equal to self.x, self.y, and then our draw. So def draw, self screen, camera x, camera y, and pygame.draw.rect, screen, self.bullet color. And then in parens here, self.rect.x minus camera.x, camera underscore x, and self.rect.y minus camera y 10 and 10. All right, and then assuming no typos, we are done with our bullets class. Let's go back over to game.py, and we said over here we had a to-do for adding bullet logic. So let's go ahead and get some of our bullets in here. Okay, so we're going to say for bullet in self.bullets, bullet.move, bullet.draw, self.screen, camera x, camera y. If check collision bullet.rect, it helps if I spell collision correctly. That is important. Bullet.rect with self.walls, then self.bullets.remove bullet. So basically, hey, if if you run into a wall, if a bullet runs into a wall, that bullet should disappear. Okay. So give me just a moment, and let's go find, I'm going to go find the fire bullets methods that we declared earlier. All right, so up here, we also had a to-do to fire a single bullet or to fire a shotgun blast. So let's go ahead and fill these in now. So fire single bullet is going to equal single bullet, self.player.x, self.player.y, self.player.direction. So basically whichever way the player is pointed. And then we want to do self.bullets.append bullet, self. And then we're just going to say add sound, not count. To do add sound. That's what we want there. Okay. And then we'll also do def fire shotgun bullet self if self dot shotgun ammo is greater than 0, directions equals self dot player dot direction 0, self dot player dot direction -10, and self dot player dot direction 10. And then we're just going to say for direction angle offset in directions bullet equals shotgun bullet, self dot player dot x, self dot player dot y, direction angle offset, self dot bullets dot append bullet, self dot shotgun ammo equals negative equals 1. So we're going to decrease our ammo by 1. And I think up here, did we ever add shotgun ammo? I don't know. Let's see. Okay, let's go ahead and declare that up here. We'll start it out at 10. Why not? We'll probably change that later. Okay, so self.shotgunammo minus equals 1. We will go ahead and add a to-do to play sound. And then we will say we don't have, and then we'll also add a to-do ammo messaging. Let's just go ahead and see. Hey, we now have the ability to hit the space bar and get our single fire bullet, but the shotgun ammo isn't working yet. All right, I looked for a moment and found what I think is the bug here. So, and part of the hint is you'll notice it says self.shotgunammo and it's showing, it's whited out, like it's not showing that it's a valid variable. So up here, and you may have seen this when I did it, I typed shotgun instead of shotgun. So I'm going to go ahead and save that, and let's try this one more time. So I'm firing single, that's all good. If I hit the tab key, that should switch us over, and you can see the log here switched to shotgun mode. And we are still not quite functional. So let's take a look at why. So I think our fire shotgun bullet method is right. Let's go ahead and exit. Okay, let's see. So we've got self fire shotgun bullet, that all looks good. Let's come down here. We know that we're getting the, I've got 2 copies of the method because I defined it and then I redefined it. That would definitely cause a problem. So let's just remove that and try again. All right, again, single works. I'm hitting tab, I've switched modes, and we now have our shotgun blasts. And eventually we run out of, we run out of bullets and it fails, although it didn't fail in the way that I thought it was going to. Let's see, I think I left out a, nope, direction looks good. So let's see, cannot access local variable directions where it is not associated with a value. For direction, angle, offset in directions. So up here, I see what I did wrong. So you notice how I'm setting directions if shotgun ammo is greater than 0. I shouldn't be executing anything in this method if shotgun ammo, or at least not these chunks. So let's just go ahead and grab these and tab them over. And actually, let's go ahead and add in, we've got our play sound as a later to do. Let's go ahead and set our out of, got my caps lock on there, self.out of ammo. So we need a new variable up here. We're going to do self.out of ammo message displayed equals false out of the box. And then down here, we're just going to call this out of ammo message displayed equals false. And then in our else statement down here, we will print out of shotgun ammo self dot out of ammo message displayed equals true. All right, and we're not going to code up the messaging in this video. I think let's run this one more time and just make sure it's still working. Again, I'm using WASD for movement. I'm using the space bar for fire, and then tab puts us in shotgun mode, and all of that is still working. So I think this is a great place to go ahead and end the video. In the next video, we will start implementing the zombies and get them to chase our player. So see you in the next video. Welcome to part 5 of Zombies and Reinforcement Learning. So in this one, we're going to go ahead and get started drawing the zombies and putting together some of the logic. So we're going to start right down under player.draw here. And we will just start with for zombie in self.zombies. And we're going to do zombie.draw, self.screen, and camera X and camera Y. We're also going to add ourselves a to-do to add draw health drops. We don't have health drops yet, so there's really nothing to draw. We're going to go ahead and draw our world boundaries for testing. So pygame.draw.rect self.screen self.border color. This should just put a nice little border around our world, minus camera X, 0 minus camera Y, and then self.world width, self.world height, and 5. Okay. And then we will go ahead and throw our walls up there. So we're going to say for wall in self.walls. We're going to do pygame.draw.rect self.screen self.wall color wall.x minus camera.x wall.y minus camera.y wall.width and wall.height. Okay. And it's not lighting up those variables because it doesn't understand what a wall is. That's okay. Let's go ahead and see if what we've got so far is working. Let's just see if we get any errors. Oh, no module named Pygame. Let's see why. Oh, I think I know what's going on. For whatever reason, it did not keep Zombie Shooter V1 as my environment. All right. And now we've got some walls and we've got some zombies. But you can see the zombies don't move and nothing happens when we shoot them, which doesn't make for a very fun zombie game. So let's go ahead and close that out. And I'm going to go and grab the zombies and the logic for our zombies. So way up, let's go up here. And we have another one of our to-dos where we said add zombie logic. Now is the time to complete this to-do. And you can start to see again where the to-dos are really useful for going back and finding what you're missing. So we're going to say self.zombies temp is equal to open braces. We're just going to create a new list for temp zombies. So we're going to say for zombie in self.zombies if check collision zombie.rect with self.bullets So this is us finding out if a zombie's been hit by a bullet. So if check collision zombie.rect self.bullets, we're going to say bullet dot equals get collision zombie.rect self.bullets, and then we're going to say self.player.score plus equals 1. So hey, you hit a zombie, you get your score has increased. And then we're going to say self.bullets.remove bullet, because it wouldn't do for the same bullet to go through more than one zombie. All right, we're just going to say to do add sounds. We'll come back and do our sounds later. And then we're also going to say to do add health drop. All right, and then elif check collision zombie.rect with self.player.rect, and be sure to put it in square brackets because this is it's intended to accept a list of rectangles for the second value, and obviously we're only passing him one, but we still need to turn it into a list. Then we can say self.player.health minus equals 1. And then we'll also say add another to add sounds here. Okay. Else self.zombies temp .append zombie. So if you think about what we're doing conceptually here, we've created a temp zombies. We're basically saying for a zombie in self.zombies, we're doing all these things, we're removing them. If, removing bullets if we hit one. If there are no collisions, so if there's a collision with either a bullet or the player, the zombie will not make it into temp zombies. If there are no collisions, then it's going to get appended to zombies temp. So now we can say self.zombies equals self.zombies temp. And we can finally say that if there were no collisions and the zombie made it in the list, now we can say for zombie in self.zombies zombie.move toward player self.player.x self.player.y and self.walls. So this should, if we get everything right, go ahead and start moving our zombies towards our player. Hey, our zombie is now running towards the player, and when we shoot a zombie, the zombie disappears. All right, that is exactly the behavior we were looking for. This is starting to turn into a functional game here. All right, and if we run into 5 zombies, 3, 4, 5. You know what? I don't think I think our health is probably in the negative, but we don't have the game over functionality yet, and we don't have anything doing the health display, so it's not telling us. We just we can soak up as many zombies as we want because we haven't told it otherwise. So let's go ahead and start working on the display section. I'm going to take just a moment and find that. Actually, let's do game over. Let's get the game over method in game here. So we're going to put that right above fill background. All right, we're going to say def game over. Let's go ahead and get that in place. And we're going to define a game over surface equal to self.announcementFont.render. And it's going to render you died, true, and 255.0.0 for the color. And that should be red text. Game over rect equals game over surface dot get rect center equals self dot window width divided by 2, and self dot window height also divided by 2. So this should put it right in the middle. We'll go ahead and say self.screen.blit game over surface and game over rect. We'll do pygame.display.flip to update the display. We're going to say a to-do here is to add noise, and we will do pygame.time.wait 2000. That's in milliseconds, just because we want to display the, the game over for a moment, and then we're going to say quit the game. So that's going to be pygame.quit and sys.exit. All right, we now have our game over method. So down towards the bottom, right under this Pygame display flip, we're just going to say if self.player.health is less than or equal to 0, then we're going to go ahead and say self.gameover. Okay. Now we also want to go ahead and do our health display. Give me just a moment to find the code for that. All right, so let's go back up to our fill background method. And we're finally going to add a little bit more to this. So back here we said set player stats. We had to do for that. And at the time we didn't have a player object. We couldn't really set stats on a player that we didn't have. So this one just kind of hung out unused. Let's go ahead and set that up. So we did self screen fill with a background color. We are going to go ahead and set up a score surface as self.font.render score, and that's going to be self.player.score true and 0, 0, 0 should be white. And we'll go ahead and do self.screen.blit score surface 1010. And then really this is going to be very, very similar. So instead of, and in fact we'll paste a few different surfaces here. So instead of score surface, let's go ahead and do health surface. And we'll do self.player.health. And we will say self.screen.blit health surface. And instead of 1010, it's going to be 1035. We're putting coordinates in here. And then this one is going to be level surface. Oh, we already did level surface. Let's go ahead and we will get rid of that. Under level surface, we will go ahead and do ammo surface. Self.font.render. Oh, and I realized we left the word score up here. we want to go ahead and turn that one into health. Our health is not our score. And then this one is specifically tracking shotgun ammo. The regular ammunition is unlimited in this game, although you could obviously change that. So that will become self.shotgun ammo, true. And then we are going to blitz ammo surface. Okay. And then finally, we're going to say if self.out of ammo message displayed and self.gun type equal to shotgun, then out of ammo surface equals self.font.render out of shotgun ammo, press tab to switch single shot and true and 255.0.0, and that should be red. Okay, and then also in the if here, we're going to say out of ammo rect equals out of ammo surface dot get rect, just like we did before. Center equals self dot window width, self dot window height, self dot screen dot blit out of ammo surface, out of ammo rect. Okay, and that should be all. So now, if we run our main method, we should have, oh, and I see we've got some things kind of jammed together up there. Let's Control-C out of this and go fix that. So the problem here is that I set 1010, 1035, 1060, and then I didn't change this one. So I've got multiple things that are kind of jamming up there in that top corner. So we're going to go ahead and do 85. I'm also realizing I missed one. We need to do, we're just going to go ahead and say gun type surface. And that's going to tell us what gun we're currently holding. Self.guntype.title, true. And then we will go ahead and blitz self.guntype.surface. No, we don't even need that. Self.guntype. It's not self, that's what's messing me up. Gun type surface. And to not repeat our mistake, this is not 85, this is 110 pixels down. All right, take two. Hey, all right. We now have a health option up there. We've got our level, we've got our ammo. Let me go ahead and change. Hey, if I hit tab, it changes to shotgun. That's cool. And it does work. And my shotgun ammo goes down. I'm going to go ahead and use all of it to make sure. Hey, and I can't use any more because my ammo is now 0. I can no longer shoot. So all of that is working correctly. Now I'm going to run into a bunch of zombies and let's make sure that the end game message works. Okay. So at this point, we have some functional, display messages. We're able to, end the game if the zombies get the character. Let's go ahead and work on our start next level method. So up here, let's just go right above, let's go right above game over. And this is going to be, you know, what changes as we go from level to level. So we're going to do a def start next level self.level plus equals 1 if self.level greater than 3, next level surface equals self.announcement font dot render u1. So we're basically capping levels at 3. We're saying that there will only ever be 3 levels. Else next level surface equals self.announcement font dot render starting level self.level true, and we're going to say 255.0.0. All right, next level rect equals next level surface dot get rect, center equals self.window width 2, self.window height 2 divided by 2. We're going to go ahead and zero out self.zombies. So self.zombies equal, we're going to blank them out, self.bullets, we want to reset each level. Oh, I messed that up. All right, and then we're going to say if self.level is equal to 2, I'm going to add a to-do here to play sounds. Self.walls equals walls 2, and self.level goal equals 15. So if you recall, we started with a level goal of 5, so you have to kill 5 zombies to move to the next level. By the time we get to level 3, so we'll go ahead and say elif self.level is equal to 3. Then we are going to have another to-do to play sounds. And we will go ahead and say self.walls is equal to walls 3. And self.level goal equals 30. And then finally, self.screen.blit next level surface, next level rect. Okay. And then we also need to go ahead, let's see, I wanted to do to add loot drops. And let's see, what else do we want? We want to go ahead and increment the zombie top speed plus equals 1. We want to do plus equals 2 for max zombie count. And then we want to go ahead and reset the player object. So we want to go ahead and say self.player equals player world height equals self.world height, world width equals self.world width, and walls equals self.walls. We just want to stick the player back in the middle of the screen. Pygame.display.flip and Pygame.time.wait. We just want to wait 4 seconds in between levels. And then finally, if self.level greater than 3, we want to go ahead and say Pygame.quit and sys.exit. Okay, let's play it again. All right, I've got ammo, I've got a goal. All right, and we are not properly going to the next level, so let's see what I forgot. You know what? We set up the start next level option, but we never actually called it. So down at the very bottom of game.py, we're going to say right after self.clock.tick, I'm going to say if self.levelGoal less than or equal to self.player.score, self.start next level. Okay, so let's go ahead and run that. Now, if we hit 5, it should go ahead and bump us to, hey, starting level 2. That's what I was looking for. And we now get a new set of maps and faster zombies and more zombies. And you can play with this as much as you'd like. You know, this was a good progression for me. This is where I wanted it to be. But you could obviously make the zombies faster or slower, or have more of them or fewer of them. And I'm just going to play this until we're able to make sure that we get all the way through level 3. All right, we're starting level 3. And now they're going to be even faster with different walls. Well, some of them will be faster. That's the unpredictability side of it, is having zombies that are randomly faster, slower, coming from different places. All right. Our score is 20. We need to get to 30 to win. And I'd like to get all the way to the win message so that we can see what that looks like. Ah. My health has dropped to 3. We'll see if I actually do win this round. Hey, and we got to a U1 message. And the game should wait 4 seconds and then successfully quit. So at this point, we're not done. There's still some features we want to add, but the game is actually playable. You've got your player dynamics. You are able to go around and shoot zombies and have them move towards you and all that fun stuff. And we effectively have a playable game. So in the next video, we're going to go ahead and get some of the bullet loot drop type things. We'll get the health drops set up, and then we'll look at sounds, and then we'll probably move on to actually getting the AI to play the game. So with that, I will see you in the next video. Welcome to part 6 of Zombies and Reinforcement Learning. In this video, we're going to go ahead and get started on the health drops and loot drops, and maybe we'll get to some of the sounds. We'll see. So let's go ahead and we're going to do class treasure chest def init, and this is going to be like an ammo pickup. We'll do self x and y to define where it needs to go. And we're going to go ahead and say self.closed image equals pygame.image.load images/chest closed.png .convert alpha self.opened image equals pygame.image.load images/chest opened.png .convert alpha We'll go ahead and say self.size is 50. Self.closedImage is equal to Pygame.transform.scale. Self.closedImage. And then we will go ahead and say self.size, self.size. And do the same thing with OpenImage. OpenImage, and same thing with size. Okay, and then we'll say self.rect is equal to Pygame.rect x, y, self.size, and self.size. Okay, and then we'll go ahead and set a default self.isOpened to false out of the box. All right, and then we will, as always, code in a draw method. Screen camera x, camera y. If self.isOpened, then we'll say screen.blit self.openedImage. Let's see. And then self.rect.x minus camera x, and self.rect.y minus camera y. Else screen.blit self.closedImage self.rect.x minus camera x, and self.rect.y minus camera y. Okay, that's our treasure chest class. We're also going to have a health drop class. Definite xy self.image equals pygame.image.load images/heart.png.convert alpha. We'll do self.size equals 30, make it a little smaller. And self.image equals pygame.transform.scale self.image, self.size, and self.size. Okay. And we will set the position based on the coordinates. So self.x equals x, self.y equals y, self.rect, not reduce, equals pygame dot rect self.x, self.y, self.size, and self.size. Okay. And then just like before, we will do a draw of self screen camera x, camera y, and screen.blit self.image self.x minus camera x self.y minus camera y. And that should be our draw method. All right, let's go. Give me just a moment to make sure I've got the right location. Okay. Let's see. In our start next level, we had it to do here for add loot drops. So we're going to go ahead and do that. We're going to say self.treasurechest equals treasure chest. And we need to declare our XY here. So that's going to be X, Y equals random.rand int 50 self.worldWidth minus 50 and random.rand int 50 self.world height minus 50. Okay, so that should take care of our initial spawn. Okay. Okay, and then let's go down to our walls section. You can see as a code base like this grows, it definitely gets more complicated to keep track of where everything is and where everything is supposed to be. And that is definitely the case here. So down under our walls section, we're going to say if self.treasurechest, self.treasurechest.draw, self.screen, camera X, camera Y, if self.treasurechest and self.player.rect.collide rect with self.treasurechest. So basically if the player found it. If not, self.treasurechest.isOpened. Then we're going to go ahead and set self.treasurechest.isOpened to true. And we will go ahead and say self.shotgunammo equals the min of shotgun ammo plus 5, 20. And so basically we want to max out at 20. We don't want to allow the player to collect more than 20. And then we want to go ahead and print ammo refilled current ammo, just to give ourselves some logging. And then if self.healthDrop and self.player.rect.collide rect, and actually this should have been collide rect as well. I let that autofill get me. Self.healthDrop.rect. Then we are going to say self.player.health is the min of self.player.health plus 1 or 100. Player health can't go over 100. Print heart collected. And self.healthDrop equals none. So we can only have one health drop. And then we also want to say, this is going to be up in the zombies. We apparently have self.zombies in many places. Let's go find zombies temp. And the top of zombies temp. Okay, so here was our to-do for add health drop. That's what we want to go ahead and do. So we're going to say we're going to add a 20% of a health drop if a zombie dies. So if random.rand int 100 is less than or equal to 20, then we're going to say self.healthDrop equals health drop zombie.rect.x and zombie.rect.y, and that should be it. Let's go ahead and test and see how these things work. So one, somewhere on the screen should be a chest, I believe. Hey, there's our chest. So it opened and we got +5 on our ammo. Now the health drops are based on statistics, based on a 1 in 5 chance. So it's not like that's guaranteed, but we should see one at some point, and we have not so far. So let's just go. I just want to make sure I actually saved this file. Let's try again. Always make sure you save before assuming code problems. I'm waiting for one of these guys to drop some health. Okay, it seems like a 1 in 5 should have gotten us a health drop by now. So let's go ahead and go take a look at the code. Okay, just for testing purposes, I'm going to remove the randomness, and we're just going to say every single time a zombie gets taken out, we want a health drop. All right, so we're looking for a problem with the health drop display. And it might be that we don't have a health drop display. So let's go up here and we find yet again one of our to-dos. So let's go ahead and clear that to-do, and we're going to say if self.healthDrop, then self.healthDrop.draw, self.screen, camera X, and camera Y. Okay, let's try this again. Keeping in mind we've still got it set to draw one every single time. And there we go. And if we run into it, our health goes up to 6. And you'll notice there can only be one health drop at a time. Okay, so let's go ahead and kill that. And again, we're going to go find health drop. And then we want to add our more random method back in. We don't want a health drop every time a zombie goes down. That would make the game too easy. So now, about 1 in 5, we should get one. Hey, and there we go. And our health went up. All right, we are just about done with the base game. Let's see. I'm going to go ahead and end this video now. In the next one, we will go ahead and work on sounds and getting sounds, properly playing in the environment for zombie bites and shooting and other fun stuff. And then after sounds, we will be at a point where we can kind of cut a release, so to speak, and start working on the AI playable version of this. So until next time. Welcome to Zombies and Reinforcement Learning Part 7. In this video, we're going to go ahead and start adding sounds. So full disclosure, you don't actually need this video at all to successfully play this game with reinforcement learning. The AI doesn't care. It's not going to take the sounds and do anything with them. It does make it a lot more fun as a human to play the game, though. So this was originally developed as a, build a human game first and then convert it for AI. So we're going to go ahead and add all of the sounds to make this one fun for a human player. And it really does, just from a playability perspective, it makes a huge difference. So let's go back up, let's go to the game.py, and we're going to go to the zombie shooter class, and right below self.sound, we're going to do another block here, and we'll say if self.sound, and we're going to start pulling in pygame.mixer.preinit. I don't remember what these numbers are for. I do recall this was necessary to get everything working correctly. And then we can say pygame.mixer.init. So the mixer is, Pygame's sound system. And then we're going to say pygame.mixer.music.load. And we'll say sounds/background music.wav. So Pygame has two main sound functions that we're going to use. Mixer.music and mixer.music.play is going to be like something that plays continually. If you run, and this is something I had to figure out getting started with this, if you start with mixer.music and then try to play another sound like a shotgun blast, it's going to replace the music with the shotgun blast. It's not going to, layer music pieces. So you get one piece of music playing at any given time. That's your background music. And then we're going to use another thing called pygame.mixer.sound that's going to, do the sound for the rest of the other sounds. So we've got music.load. We're also going to say pygame.music.play. -1, 0, 0. And then we are going to have, we actually need to slow down our walking sounds. I'll show you why a little bit later. Equals 0. And let's go ahead and load up. Actually, let's just start there. Let me show you what we've got so far. So now, if I run main.py, Pygame has no attribute music. What did I do? I forgot to run mixer. Music, mixer dot music. Okay, let's try it again. Hey, now we've got our slightly creepy background music, but everything else is still quiet. All right, so we got our creepy background music. Let's start building in the other sounds. So let's go ahead and do, I wanted to kick things off with some vocals. So let's go ahead and actually let's declare all the sounds first. So we're going to do self.zombie_byte is pygame.mixer.sound, and we're going to say sounds/zombie byte 1.wav. Okay. And then let's just copy this. We'll copy it about 8 times. Okay. Okay, so here we're going to say zombie hit, and then instead of zombie byte 1, it's going to be zombie hit.wav. And all of these sounds files were provided in the original project, the starter project you downloaded. It is worth noting all of these were from open source music sources. I would love to link to them, but as I built out the game, I kind of lost where I pulled everything from. So they were all legitimate, they were all open source. I can't credit the original creators. And if I find it, I will put it down in the video description. So we're going to say this one is Shotgun Blast. Shotgun Blast.wav. Okay. Under Shotgun Blast, we're going to do Zombie Snarl. Here we're going to do Footstep. We'll do Footstep.wav. Under Footstep, we're going to do Vocals 1. And then this is not Vocals 1.wav. I named them after the words. So one of those things got in. We'll do Vocals 2. And that's going to be sound/virus infection alert. You can tell I had some fun with this. Vocals 3 is going to be let's see. I actually don't think I used the rest of the vocals. We'll find out. We'll see where that lands. Okay, I think I just did vocals 1 and 2, just seeing how, well, we'll go ahead and, no, we won't. Sorry, I've got vocals 1, 2, 3, and 4 in the original code base. Let me go see if I actually used vocals 4 anywhere. Nope. Hey, okay, I did use vocals 3. Equals pygame.mixer.sound sounds/come-and-see.wav. Okay, and then we want to go ahead, since this is our init method, this is where we're kicking everything off. We want to go ahead and do self.vocals1.play, and that's kind of our kick off the game sound. So let's play it and see what we get.
One of those things got in. Kill it.
All right, and what you should have heard there is a one of those things got in. Kill it as we started the game. Okay, we're good. Let's close it. And let's go find all of our to-dos. Because at this point, most of the to-dos should be sounds. They should be, you know, let's see. All right, so self level 2, we're gonna do self.vocals2.play. And self level 3 is going to be self.vocals3.play. So basically every time we do, you know, a new level, we want to go ahead and make some noise. The game over method is going to have a zombie snarl. So I wanted some kind of self.zombie snarl.play. Okay. And then and by the way, when we get to the AI portion of this, we're going to make a lot of these conditional. Again, that's going to be part of the conversion process. That's something we'll need to think about as we, you know, do AI things with this code base. Let's go find our next to do. Hey, fire single bullet. Let's see. All right, so fire single bullet. We'll get a self.shotgunblast.play. And then fire shotgun bullet will also get a self.shotgunblast.play. Okay, let's go ahead and stop now and run it and see if we're starting to get the sounds we want.
One of those things got in. Kill it.
All right, we got our intro. Hey, and zombie goes away. And we get our sounds. Okay, we don't get any sounds when the zombie gets in.
Virus infection alert. Warning.
So you'll notice our change level sound played there. That was pretty cool. All right, let's go ahead and end it and go find our next to do. All right, we'll get the toggle pause method later. Let's see, play walking sound. Let's say self.player.y. Okay, let's see. All right, we're going to do self.play. Oh, we don't even have a play walking sound method. All right, let's go ahead and just put this here. And let me go locate our play walking. All right. We're going to put it right above start next level. And the reason we're putting play walking sound in its own thing is I needed in its own method is I needed to wrap a little bit more logic around this. I needed a way to rate limit it. So if self.sound current time equals pygame.time.getTicks. And you want to use Pygame's time, not like system time, because your game might be going faster or slower. If current time self.lastPlayWalkTime is greater than 1,000, self.footstep.play. If you don't put this, it just ends up sounding really weird as the player walks around. Equals current time. Okay. So let's run it.
One of those things got in. Kill it.
Hey, we get our nice walking sound going side to side. We don't get it going up and down. So I think we have another to do. And it's right here. Okay.
One of those things got in. Kill it.
Hey, now we get our walking sound going up and down and side to side. All right. We're getting there. let's go find our next to-do. And this is going to be under our check collision for zombie in self.zombies. Let me go pull that one. Okay. So here we're going to say, if self.sound, self.zombie hit dot play. And what this should do, so you'll notice this is in the check collision section with zombies and bullets. So this should create a nice little sound when we hit the zombies. Yeah, that's what we're looking for.
Warning. Virus infection. Alert. Warning.
So we also want, let's keep going with our to-dos. Okay, and this is the zombie, the check collision for zombie rectangle with self-player rectangle. So let's go find that. All right, so this one's going to be our self.zombiebite.play. Okay. And let's go ahead and just to make it easier for ourselves later, we'll do if self.sound. And we want to do our zombie bite play.
One of those things got in. Kill it.
There we go. All right, so now we get a nice little noise when the zombie gets to the player. All right. Let's see. I think we found one more to do in here. To do. All right, and that was implementing our toggle pause method. So let's go ahead and just do that. All right, so we're going to say self.paused equals not self.paused. So automatically we're just going to go from one to the other. And we're going to say if self.paused, then pause surface equals self.announcement font.render game paused true and 255 255 255. Pause rect is equal to pause surface dot get rect center equals self.window width over 2 self.window height over 2 self.screen.blit pause surface pause rect and pygame.display.flip. So that's updating the display. All right, while self.paused for event in pygame.event.get if event.type equals pygame.quit pygame.quit sys.exit elif event.type equals pygame.keydown and event.key equals pygame.k escape self.paused equals false. And then self.clock.tick 10. All right, let's go see if our pause function
One of those things got in. Kill it.
works. So now if I hit escape, the game gets paused. If I hit escape again, the game gets unpaused.
Warning. Virus
And we get all of
infection.
our sounds,
Alert.
we get our background
Warning.
music, we get our shotgun sounds, we get our zombie bites. So yeah, at this point, the base human playable game is done. We have successfully built our zombie game. And then in the next video, we're going to go ahead and start, converting this over to something that an AI is going to be able to play. We're going to start turning it into an OpenAI gym environment. Couple things. So as we convert it to be playable by AI, it's going to become a little bit less playable by humans. This is a really good place to go make a copy of the project because, we're going to start iterating away from something that's easily human playable. So if you want to keep this around, if you want to be able to use it for other things, or frankly, just play it at some point, go ahead and copy the project off, create a copy that we're going to use just for AI. Finally, if you have stuck with me this long, if you've coded everything out and you're enjoying the series, do me a favor, go hit subscribe, go like the video. It really does help me, create more of these things. So yeah, I hope you're enjoying what you're seeing so far and are having fun coding along with this. And I will look forward to seeing you in the next video when we start converting this game for AI. Until next time. Welcome to Zombies and Reinforcement Learning Part 8. So we've hit a critical milestone here. In Part 8, we're going to go ahead and start converting this game over to something that an AI can play. That's going to be, turning it into a compatible OpenAI gym interface. Something I meant to say in the last video, if you have questions, if you want to talk about AI or reinforcement learning or robots or any of the other fun stuff, I do have a Discord. I will put that down in the video description. You're welcome to come join and talk about and ask questions about the videos and, generally hang out with tech people. So let's go ahead and get started here. First thing I'm going to do, I'm going to go ahead and commit this to git latest working game. All right. And then I am going to come out of this, and something I suggested in the last video, and I'm going to repeat it again. This is a great time to go ahead and make a copy of the project. So, we've created something that a human can play. It's functional. And we need to go ahead and we're going to start making some pretty substantial changes to make it something that an AI can comfortably play. So if you want to keep the human playable version and keep it functional, go ahead and start work on this next phase on a different copy of the project. So, if you're comfortable with Git, feel free to go stash it in a branch or something, or tag it. If you're not, copy it to a second version. I'm going to go ahead and call this Zombie Shooter V1 AI. And that is the version we're going to be playing with from here on out. So goodbye, original Zombie Shooter project. You will be missed. And just a reminder, at this point in the course, you should have a fully functional zombie game that you as a human can go play. So I am just going to go and open up the other copy of this project. And we can start working on it. All right. So the first thing we're going to do, So let's talk conceptually about what we need to do before we start coding it. So right now we have a main function that has a game loop that's just running game.step with no params. We want to be able to pass in, and if you haven't worked with OpenAI gym environments, they have a step method. So they have a step method that takes an action, and that step method is going to return state. Let's see. I should have this memorized. All right, that is going to return state or observation, reward, done, and info. And then there's another parameter that we almost never use. So you're going to end up with something like this. It's also going to need an env.reset function. And that env reset function is just going to return state and info, and it doesn't take any parameters. And that's going to basically start the game over. So we need the ability to pass a step into our game, and then we need the ability to get data back from it. We need some pre-processing capabilities, so we need the ability to go and take images, take image data, and turn it into something that's we can feed to the AI. So there are a few different things we've got to do here, but conceptually, let's just start. I think the first thing we need to do is to be able to interact with the game from outside. So we can't deal with Pygame events in the game loop. Our AI player isn't going to understand how to work with those. So we need, in our step method, if I can find it, here we go. We need to be able to take a parameter that contains all of this data and turn it into, in this case, a numerical representation. So let's go ahead and for now, what we're going to do in our main.py is we're going to make our main.py sort of the human interface for the machine playable game. So let's start there. So we need to grab this entire block in step. And copy it. And you're going to come over here to main.py, and in the loop, we're just going to go ahead and paste. And it is way too far over. Let's see. We want to pull that for statement, and then let's go ahead and import Pygame, import sys. Okay, and then this will all go. You don't have to worry about that just yet. So over here, we're going to go ahead and delete. To do, add inputs. We're also going to go ahead and grab our keys get pressed. Okay, we're going to need that over here. And we can remove it here. And then we're going to need our, this one's probably easier to just go ahead and type out a little bit. So over here, under keys get pressed, we're going to, first off, up at the top, go ahead and do action equals 0. So we're starting out with an action of 0. We are, the Pygame.quit we can keep. That's fine. So in here, we're actually going to give our actions numbers. And you could do this a few different ways. This is how we're doing it for this one. So we're going to say if event.key equals ktab, then action equals 5. If event.key equals kspace, and get rid of all this logic, then action equals 6. If event.key equals kescape, then action equals 7. And we're going to come down here and say if action is still 0, so basically if none of these other things triggered, then we want to check the rest of the keys. So we want pygame.kw, action equals 1, and this is getting our movement. We don't want to get rid of a, like a fire command in place of a movement command. And you'll notice that as a human, this will feel a little bit less smooth to play. It definitely will be, but it makes it a lot easier for your autonomous agent to get in there and do its thing. 3, if keys pygame.kd, then action equals 4. All right, and then at this point, we now have all of our actions set up, and we can pass in a action equals action. All right. So let's come over here and go ahead and start to set up our game to be what it needs to be. So we actually don't need self.pause anymore. I don't believe we need player moved. Let's see. Don't think we need it. We do still need the length. Oh, never mind. We need our self.paused. We'll keep that. We don't need this stuff. All right. So we're going to go ahead and do some action mapping. And we could just go based on numbers through the whole thing, but I find this a lot easier to read and work with long term. So we're going to say up equals true if action, oh, we need to take an action here. Action, there we go. Up equals true if action is 1, else false. And just copy that a few times. Down equals true if action is 2. Left equals true if action is 3. Right equals true if action is 4. Switch gun. And I'm going to leave this as an exercise for you to, work with on your own if you'd like to. I actually found that including the ability to switch guns made the game far too complicated for the AI to play. It was never able to fully understand that once you switched into shotgun, you would eventually run out of ammo, and that you could no longer, shoot at things. And that resulted in a sporadic, confused training pattern, because it would lose. It almost felt like it was losing the ability to recognize that firing a bullet at a zombie was good, because sometimes when it took that fire action, it didn't actually make it all the way through, because it had run out of ammo, and it wasn't smart enough to figure that out. So I'm going to set this to false statically for the remainder of this course. This is definitely, though, like I primarily made this video series to talk about creating custom environments, and I simplified it to get it working. You could probably use something more advanced than double Q learning and get around this. So there's a future exploration for you. So I'm going to say fire equals true if action equals 6. This would be action 5. So we're basically nulling out action 5 on purpose. And we're just setting pause equals false statically. Okay, so pause will always be false. All right. So let's go ahead and let's see. We can get rid of. All right, we actually don't want to get rid of the self.player_speed stuff. So let's go back. Let's see. Well, I'm going to save this. And I think I deleted one more thing than we needed to. This is the lovely thing about having all this in Git. I'm just going to revert that block because we do still need it. And that should be good. We don't need it in its current form, but it's going to be a lot easier to, go back and fix this way. So instead of, keys KA, we're going to say if left. Instead of keys KD, we're going to say if right. If keys KW, we're going to say if up. If down, simple enough, right? And let's go ahead and see, we haven't coded everything, but let's go ahead and see if this basic functionality
One of those things got
working.
in. Kill it.
Okay, so I can move around successfully. I can't shoot anything, but I can move. Okay, so we're making progress. Let's see. Let's go over to our game again. And what I want to find is all right, I think I removed, let's go back over to Git and see if I pulled the fire section. I don't think I did. All right, so this falls firmly under, I was looking straight at it and didn't see it. So our fire logic was here. So we're just going to go ahead and retype some of that. So back down here under step, because it is going to be a little bit different. So we're going to need a variable up at the top that's self.lastBulletFrame. So let's go ahead up here, and we're going to say self.lastBulletFrame equals 0. So why are we doing that? Well, a human has some physical limits to how fast they can fire a single button in a game. The AI really doesn't. So if the game can run at, say, 60 frames per second, the AI has no problem running, firing 60 bullets per second, 1 per frame, which is a great strategy for winning, but it does kind of defeat some of the game mechanics we're trying to get here. I don't just want the AI to be able to fill the entire screen with bullets in all directions and that be how it wins. So what we're going to do is we're going to say if fire and self dot, we also need a total frames. We'll get there. We'll start with 0 for both of those. Okay, so we're going to say if fire and self.total frames minus self.lastBulletFrame is greater than 10. And then we'll say if self.gunType is single, self.fire single bullet, else self.fire shotgun bullet. And then down here, we'll go ahead and say self.lastBulletFrame equals self.total frames. And then we will also need, we kind of statically coded the switch gun to false, but let's go ahead and add the logic if you want to change that later. So we're going to say if switch gun self.gunType equals single, if self.gunType equals shotgun, else shotgun. Okay, so one of the things we're going to need to do is go ahead and add a human option or a human variable to our zombie shooter here. So we're going to default to human equals false. Okay. And then we can do, and we're going to start to change certain things based on whether a human's playing. So self.human equals human. Okay. Now let's go down to Pygame. Let's see. We're going to need to change our clock tick. So that's going to be towards the very bottom. So what we're doing here is we're going to say if self.human, then self.clockTick is self.fps, which we passed in as, say, 60. Else, we just want self.clock.tick, which will basically make the game run as fast as possible. So over here, we're going to go ahead and say human equals true, because we as the human are playing the game. Human equals true. But what I was looking for was actually where we're setting total frames. So give me just a moment to find that. Okay, so in the very beginning of the step method, we're going to go ahead, before we do anything else, we're going to set self.totalFrames plus equals 1. All right, let's go test this out. We should, at this point, be able to
One of those
fire.
things got in. Kill it.
All right, so we now have a step interface
Warning.
that
Virus
is
infection.
successfully
Alert.
allowing us to interact with our game. All right, let's go ahead and one of the things we need to do is make sure that disabling sound works across the board. We do not want to engage the audio system when we're playing the game as fast as possible. So let's go ahead and we're going to start by just making not human a shortcut for no sound. So we said sound equals sound, human equals human. We're actually going to change some of that logic just a little bit. We're going to say if self.human, then self.sound equals sound, else self.sound equals false. Okay.
One of those things got in. Kill it.
Okay. Didn't quite, because we played it as human. I am going to change this to human. Oh, that's already defaulting to false. Let's go over here to main, and we're going to change human here to false. Now it's probably going to go really fast. Let's see. Yep, so this is how the AI would play it, by the way. This is what it, and we lost. But you notice it failed out because it said no attribute shotgun blast. And it did that because we probably don't have the right logic around, yeah, we don't have a if self.sound. Okay, let's just go look for all of the other instances of play. Let's do a better search. Play. Okay, so we want to go ahead and say if self.sound. Okay, that's already wrapped in the self.sound. Okay, so we want this to have a if self.sound. Okay. All of that. Yep, this needs so basically just go through and, or you know what, I think we've already got that logic in play walking sound because I didn't hear a walking sound earlier. So let's go run main again. All right, zombie snarl apparently. And you'll notice I'm just basing it off the error. Zombie snarl. Oh, it helps if I'm in game. Okay. If self.sound. All right, and let's try that one more time. Hey, and we seem to have no sounds. All right, I'm going to say that's a really good place to end this video. We're getting close to the 30-minute mark. In the next video, we'll start talking about processing observations and actually getting data back from the environment. But at least now you have an environment that you can work with externally. So until next time. Welcome to part 9 of Zombies and Reinforcement Learning. So today we're going to be finishing up the conversion of this environment for OpenAI Gym. That's going to include some observation methods, as well as some changes to the step method, so that we can start to get observations back from the environment for our AI to learn on. I'm going to go ahead and preface this and say that I am getting used to a brand new keyboard with a different layout. So my typing is going to be a little bit slow today. If you need to speed up this video, I completely understand. All right, let's start out with our first goal, just so you can kind of understand it from that side. So when we start our game, one of the first things we should need to do is call game.reset, something like that. And game.reset should reset the score to 0. It should, reset lives to 5. It should basically go back to the beginning of the game. It should also return an initial observation and info. So we should be able to get something like that from game.reset. Further, every time we call game.step, we should be able to get a series of items returned. So step should return observation. It should return reward, done, truncated, and info every single time. So when you call reset, you should get observation info. When you call step, you should get all of these things. So let's go ahead and start working on some of those methods. So inside of game.py, we are going to need we'll start with an underscore get info. So these are methods that are defined by the OpenAI standard. We're going to do get info, self, okay, and then we're not actually going to use this info set, but we're still going to go ahead and code it out. We're going to say gun type num equals 1 if single in self.gun type else 2. Okay. And what getInfo is supposed to do is it's supposed to return a numerical representation of information about the environment that's not available in the main image observation. So this is if you want to return, additional things that you want the agent to know. We're going to train it without any of this, but if you use a different type of agent or you want to build a different architecture, this could be useful to you. So, and again, the whole point is that we're defining a full, a full environment here. So we're going to return health is going to be equal to self.player.health. Okay. We will define shotgun ammo as self.shotgun ammo. we will define gun type. And I defined that gun type num up there because I felt like a number was an easier. We'll go ahead and return self dot gun type as a, as a text value, but I also wanted to have gun type num, just because if you were using this, as a model input, it's going to understand a number a lot more easily. You won't have to convert it ahead of time. Okay, and then we're also going to return the length of self.bullets. And again, we didn't use this, but you could conceivably need to tell the AI how many bullets are already out on the screen. One of the early things I was playing around with was capping the number of bullets instead of the bullet rate. So basically saying, hey, you can only have 20 bullets. That's not how we ended up doing it, obviously. We did a rate limit. But if I'd stuck with that, this would be very useful. All right, and then we need a similar def underscore get obs for get observation. That will also take self. And this is where we're going to actually pull down a copy of the screen from Pygame. So we're going to say screen array equals Pygame dot surf array dot pixels 3D, and we're going to pass in self dot screen. Okay. We are going to transpose this to the appropriate height width channels. So screen array equals np.transpose. Oh, and you know what? We need NumPy. So I'm just going to come up here to the top, and we're going to import NumPy as np. Okay. All right. All right, so now we have NumPy. We can do NumPy.transpose. And we're going to pass in screen array. And then we're going to pass in parentheses 1, 0, and 2. All right, now what else do we need to do? We don't actually want to hand the AI a full colored, full-sized image. We want to hand it something much simpler for it to learn on. So what we're going to do here is we are going to downscale the image. So we're going to resize it. We're not going to resize it as small as we might something like Pong, because it is a little bit of a more complex game. If you bring it down to 64 by 64, there's not really enough information to play it. So we're going to do 128 by 128. A good way to tell if you've scaled something down too far for an AI environment is to actually print the image out and to see if it's something that a human could play the game on. Maybe not play the game on comfortably, but like looking at it, you see that there is enough information for you to play, even if it's, tiny and on a small screen. So I found that number was 128 by 128. So we're going to do downscaled image equals CB2. Oh, and we need CB2. So let's go back to the top. And we're going to import CV2. Let me see what that import is. Nope, it is just CV2. Okay, let's go back down to our observation, our getObs. So we're going to say CV2 dot resize, and we're going to pass in screen array and the size, which is 128 by 128. And we are going to go ahead and pass in interpolation equals, and this will be cb2 dot inter nearest. And I'll be honest, if I remembered what this did, I would tell you, but I do not. Okay, downscaled image. Now we want to go ahead and cast it to grayscale because we don't actually need all those pixel values. We just need a basic grayscale image for the AI to learn on. So I'm going to call this grayscale equals cb2 dot cbt color, and we're going to say downscaled image and cb2 dot color, RGB to gray. All right. And then finally, we can go ahead and turn that into an observation that we can return. So observation is going to be equal to torch dot, we also need torch. All right, I probably should have looked at some of my imports before we got started. So we're going to import torch. Let's see. Okay. Okay. All right, so here we are going to say return, observation equals torch dot from numpy, and this will be grayscale dot float dot unsqueeze. And we're going to unsqueeze on dimension 0 there. And then finally, we can just go ahead and return observation. Okay, so our getObs method is done. All right, so the next thing we need to do is we are actually going to modify the step method a little bit. So let's start by just going ahead and doing our returns down here. So if we're in step, and we're only going to return 3 things, and I'll explain why in a moment. So we're going to return reward, which hasn't been defined. We're going to return self.done, and truncated. All right, and we need to do some defining of some of these things. So we want rewards in a few places, and this is one of those things that's you know, you can kind of play with a little bit. I'm not going to pretend that the way I've got it set up is the best possible way for an AI to learn. It just happens to be how I set it up. So at the beginning here, we're going to go ahead and start out all three of these values. So we're going to say reward, truncated equals 0, and false. Let's see. Initial observation. I'm looking at my own code and wondering why I put the false there. Oh, because I'm not being smart here. We're setting truncated to false and reward to 0. That was a dull moment. All right. So we need to think about what values we might want to include a reward. So the first thing is probably if we hit a zombie, right? So let's go ahead and say self.player score. So somewhere in here, score. There we go. That's what I'm looking for. So right under here, we're going to go ahead and say that if the player score goes up by 1, we're going to say the reward is plus equals 1. The other places, and you could, you know, if you were working with a more complex agent, which we're not going to be, you could say that it should figure out that things like hearts are bad, and maybe it should figure out on its own that hitting a zombie's bad. We're not going to do that. We're just going to go ahead and tell it right here. So if self.playerHealth goes down, we're going to go ahead and say reward minus equals 1. So if you get hit by a zombie, you get a negative reward from the environment. If you hit a zombie, you get a positive reward from the environment. All right, and then let's go ahead and find treasure chest. We also want to go ahead and say if it was able to open the treasure chest. So if not treasure chest is open, we're going to go ahead and say reward plus equals 1. So we want it to, you know, get a little positive bump if it finds ammo. And then we also want to do the same thing under health drop. So we're going to say reward plus equals 1. Okay, so that covers our rewards. Let's see if we had a done option in here already. All right, we have not defined self.done. So we're going to come up here to the top and go ahead and say, let's go ahead and define our reset method, because this is going to influence quite a bit of this. So let's go up to the top. Well, not quite the top. Let's go up to the top of zombie shooter here. And we're going to go ahead and define a reset method that a lot of these things will go into. So down under init, and we're going to call reset from init. So we're going to go ahead and in here, let's see, how much of this do we just want to move down? Not all of it. We'll get there. Okay. So def reset and that will take self like everything else. And in reset, we're going to say self.done equals false. We're going to say self.level equals 1. Because remember, this is supposed to take it all back to square one. That's the goal here. We're going to say self.level goal is equal to 5. Self.max zombie count is equal to 5. Self.walls is equal to walls 1. Self.player, nope, not play walking sound, player is equal to player world height equals world height, self.world height. World width equals self.world width. And walls equals self.walls. Okay. We'll do self.player.health equals 5. We will do self.max zombie count. We'll also go back to 5. Self.zombie top speed will be equal to 1. Self.total frames will be equal to 0, because again, we're resetting. Self.last bullet frame will be a 0. Self.shotgun ammo will be a 0. Self.out of ammo message displayed will be false. Self.gun type equals single. Okay. And then we're going to go ahead and set self.bullets to nothing. And self.zombies will also be equal to blank list. And then finally, we're going to use those other methods we just set up, and we're going to return self._getops and self._get_info. Nope, not getops, get info. All right, there we go. All right, so that part looks good. So let's go ahead and go up back into our zombie shooter here. So we don't need a few of these things now. We no longer need self.out of message displayed. Out of ammo message displayed, we're going to get rid of that. We're going to get rid of bullets, zombies, zombie top speed, level 1, last bullet frame, total frames. I think we still need self.human and the sound configuration. That's fine. But now we can go ahead and say self. We'll need a couple of, actually no, we don't even need to capture the return values. We don't need them here. So we can go ahead and say self.reset. That way we're not duplicating code. All right, we're making progress. Now, the next thing we need to do is we're going to go back, well, hang on. I think we need to do one more thing with that done flag. Let me find it. Okay, this is what we need to do. So under the start next level, right above, instead of saying pygame.quit and sys.exit, we are actually going to comment those out. Let's see, because we don't need them anymore. And we're actually just going to say self.done equals true, because we don't actually want to quit Pygame. We just want to, hey, return a done so that the AI knows that it can start the next match. All right, so at this point, everything in our get info here, or everything in our step function, should be getting a value. All of these things, it should be getting a reward, it should be getting done, it should be getting truncated. So the next thing we want to do is we actually don't want the AI to have to play every single step. So this step method is going to return once per frame. And that's a lot. Like that's going to return with very, very little movement each time. It doesn't actually require, we don't need the AI to have an input for every frame of movement. We want it to play, a little bit more like a human would. And some of that is a lot of it is just efficiency. If you're passing in 4 times as many frames, but it's not actually, there's nothing new in each one, then you're just filling up your buffer and using memory for something that's not actually training the agent to do anything. So what we're going to do, we are going to actually rename our internal step method to _step to show that it's internal. And we're going to define a new step method that's in charge of that looping function. Okay, so this is going to take step, action, and then it's going to take a variable called repeat, which we will default to 4. Okay. And and you know what? I'm doing something weird here. I don't actually want to edit this one. I'm editing the wrong step function. All right, leave your original step function alone. We're going to come up here and do repeat equals 4. Okay, and then inside this step function, we're going to track total reward, and that will start at 0. And we're going to say for I in range repeat. So basically, do most of the same thing every time. So we only want to repeat. So let's think about what we're doing. So we're going to go ahead and call it the first time. So we're going to say reward done truncated equals self dot _ step with action. Okay. So after that, we're going to append, because we're looping 4 times. So we're going to append total reward, or reward to total reward. Now we actually want, if the action is a fire, if it's anything except for movement. So things like 5, 6, which I think we mapped to. Let's see. We were going to map 5 to switch gun. We set that statically to false, but we'll go ahead and cover it here. and then 6 is fire. So we actually want to set action to 0 at this point. We've already, so let's say you hit fire. You don't want it to fire 4 times across the next 4 frames. You want it to fire once and then, let that bullet travel for 4 frames. So that's what we're going to do. We're going to go ahead and say if action is equal to 5, or action is equal to 6, then action will be equal to 0, which is no movement. And then we're going to say if done, go ahead and break. Okay. And then this is also why we did not need to return an observation earlier. So at the end, we're going to go ahead and say return self.getObs. Total reward. Done. Truncated. Self.getInfo. Okay. All right, and then this should actually be somewhat testable. So let's go ahead up here. I'm going to say human equals true and sound equals false. I don't want any sound, but I do want it to run at a, sort of human scale here, human speed. And then I'm going to say we're going to print out, let's just start by printing observation. I want to make sure that we're getting the value that we think we're getting. Okay. Let's start there. Oh, no module named CP2. All right, let's go ahead in here, and we are going to go ahead and do CP2, and then also I think we left out NumPy. And then down here, I'm just going to do pip install -r requirements. Let me see what the actual name of that is. It's not CP2 apparently. OpenCV-Python is what that's called. Okay. Now we're successfully installing CV2, hopefully, and apparently updating Torch. Okay, it's still thinking about it there. So we're going to write a little bit of extra. Oh, there it did. It went. All right. Let's go ahead and run it and see if we succeed. Okay, so we're still able to navigate around the environment. You're going to find that this feels a tiny bit clunkier with the step repeat in. but it's not awful. It's just a little more clunk than it was with the original game. And that's okay. Again, this is the version that we're making it easier for the AI to play. Let's go ahead and we're gonna Control-C out of there. Let's go ahead and print out the rest of our variables. So we're gonna go ahead and do, let's do this. If reward, this is gonna be temporary code just for testing. So if reward is not equal to 0, we're going to go ahead and print, let's see, reward, and we're going to make that reward. I don't want it to just be streaming information, but I do want it to confirm that we're getting the values that we think we are. So we're going to say done equals done. And I don't really care about info. And then what we're going to do is we're going to go ahead and write an image to disk here. So let's create a directory. We're going to call it temp, T-E-M-P. And then we're going to say image array is equal to torch. We probably need to import torch up here. Okay. Also helps if I spell it right. So we're going to say torch dot clip. And then we're going to say observation, and this is just turning it into something that we can actually print to disk here, or dot squeeze. On 0. Okay. And then we're going to do 0, 255. Dot numpy. And we're going to say as type np dot, yep, let's come up here and import numpy as np. That's going to be required. And again, spelling. Spelling is important. Okay, so now we have NP. So we're going to do this as uint8. And then finally, we're going to say result. This is just to capture whether it was successful or not. We may not need this. CV2, which we also need up here. Import CV2. I am right. And we're going to say temp slash screen dot jpg. Okay. And then we're going to feed in the image array. And there are lots of things that can get messed up here. If the channels get messed up, your image could be rotated in a weird direction. You know, you could have things in the wrong spots. Like, this is a really good check to run just to make sure that everything is working up to this point. Okay, so we're cruising around. We haven't had a score, so we don't expect it to print anything. Okay. So that gave us a reward equals 1, which is interesting. Hang on, let's try that again. Okay, no, reward equals 1. So you notice down here that it's not consistently printing when we hit a zombie, and it should be printing every single time there's a reward. See, it printed on that one. Okay, let's go see what's wrong. Something is broken. So, this is the problem. So right here it says total reward equals reward. So it's only printing if reward is the last one in the count. So let's go ahead and fix that. So that should be a plus equals. All right, let's try it again. And also let's go check our temp screen. Okay, that looks pretty good. We'll do it again in a minute and just make sure that it's, you know, in the right direction. All right, so now, all right, cool. We get reward equals 1. We got a heart collected, and that did reward equals 1. Let's let a zombie get us, and that gave us reward equals -1. And let's go look at screen. Okay, and this does look right. So we've got our wall down here. We've got our zombies, you know, where we expect them to be. You know, that looks like we expect it to. And you can kind of see what I mean about, you know, is the observation the right size for a human to be able to do something with it? And this kind of is. Like, it's not, clearly we're not getting the full features of our zombies. We're not getting the full features of our player. But you can tell which way the player's pointed. You can see the, you know, the shotgun direction. You can see where the zombies are. We should be able to see bullets if we, you know, were to go and shoot some bullets. This is enough information for a human to be able to, you know, figure out what's going on. It's not going to be enough information for the text to appear. You'll notice the text up here gets pretty mangled. So it's not going to be able to figure out how many lives it has, or that kind of information. It's just going to be able to see, you know, where zombies are and all that fun stuff. So if you needed the AI to have some of that other information, which we won't for what we're doing, but you could, that is where the info stack is going, or the info return is going to come into play. So I think we can go ahead and say this is working. We've got our rewards back. We've got our image observations back. This is actually in a spot where we could go and start to train our AI on it. So I'm going to say that's a great place to go ahead and stop the video. In the next video, we are going to go ahead and start coding out our AI agent, you know, our buffer, the rest of the program, to be able to train an AI to play this game. So I will see you next time. Welcome to part 10 of Zombies and Reinforcement Learning. In part 10, we're finally going to move from the zombies portion of this to the reinforcement learning portion of this. And the first thing we're going to do is build out our buffer.py, our buffer class. So just as a reminder, when you're dealing, and we're going to be using a double DQN. So, you know, standard Q-learning. Q-learning is going to take an observation from an environment, and it's going to directly predict the results of, it's going to directly predict the value of a given action in a given state. And then it's going to use that prediction to go in and take an action on the environment. So let's talk about how the buffer plays in for a moment. So in Q-learning, we're going to have our agent. And we're going to have our environment. And I'm also assuming, again, the whole focus of this has been building custom environments for OpenAI Gym. I'm kind of assuming that you're not a complete beginner to Q-learning. This is not intended to be a full, how to do DQN course. There's much better content out there for that. I'm not going to try to recreate it. But we'll just do kind of a quick map out of what we're doing. So we have our agent is going to be taking actions on the environment. The environment is then going to return an observation to the agent. So agent takes action, environment produces, and hopefully you can see that well enough. Here, let's blow it up a little bit. All right, so agent takes an action on the environment. Environment returns an observation to the agent. The agent is going to take that and store it in a replay buffer. So this is the actual, action happening. This is no learning is happening in this. This is agent, environment, observation, back to agent. The agent is then storing that in a replay buffer. The training process, so we'll just call that, we'll say this is the learn method. Learning. The learning process is going to take a batch from the replay buffer. So we're basically taking a, a lot of what we end up doing in reinforcement learning is taking an unsupervised problem like, RL in an environment and treating it like, a supervised learning problem. So the learning process is going to pull a batch of observations with rewards, info, etc., from the replay buffer, and it's going to, go and process that, check the value. We're going to get a loss. It's going to use gradient descent to try to improve that loss value, and then ultimately it's going to update the weights of our agent. So I'm going to say weights update, which will then use the new policy in taking actions into our environment. So this is going to be something that runs every single step. This is something that's going to be running in batches off of the main process here. So that's what we're putting together. We're going to go and code that replay buffer class, which is going to allow our agent to store observations. So with that in mind, let's go ahead and get to it. So we're going to do new file, buffer.py, and in buffer.py we're going to need numpy and torch. So we are going to say import numpy as np and import torch. We're going to call our class, so we're going to say class replay buffer. And we're going to define our init method. And it actually needs a few params here. So we're going to feed in max size. So how big can your buffer be? We're going to feed in input shape. N actions, so number of actions, and device, which we will default to CPU, but is probably going to end up being CUDA a little bit later. All right. We don't need that pass anymore. We're going to go ahead and say self.memSize equals max size. Okay. We're going to say self.memCTR is equal to 0. We're going to say self.state memory is equal to np.zeros. So conceptually, what we're going to do here is we're going to go ahead and declare NumPy arrays of our target size. We're not going to try to build, we're not going to build these dynamically as we go. We're just going to reserve, one big block of memory for our buffer, and that's going to be much more efficient than trying to dynamically expand that. So we're going to say np.zeros and self.memSize. We're going to do star input shape, and then we're going to set dtype equals np.uint8. So I want to talk about this for a moment. So np.uint8 is going to force this to be an integer value, which is what we want in this scenario. Later on, we're going to normalize our images. So that's going to take, a value that's over it's basically going to take a max image size. So let's say earlier we saw 117 as a value that comes out a lot. That's I think that's our orange background. So what normalization will be, and you don't have to type this out with me, I just want to show you something. So I'm just going to say img equals 117. Obviously it'll be an array of 117s. So normalizing this, norm will be 117 divided by 255, because that's our max pixel value, and then we're just going to print norm. Okay, again, we're going to get rid of this code in a minute. I just want to show you something. All right, so that's going to turn it into this 4588235, etc. number, and we do that to stop large values from from impacting the network, because a neural network is just a series of matrix multiplications in the background. If you pass in massive numbers like 254, it may lose the context of what that is, and you just end up with a large number overpowering a small number. So normalization helps avoid that. Now, where's the problem here? Well, we're going to store as int, but we want our network to use these. Well, why don't we just store as float, and we can store this entire float value? The reason we don't store as a float, and I actually started out with this, is if you store this as np.uint8, then your total buffer size with 500,000 images is going to end up being about 16 gigs of memory. And in fact, if you have less than 16 gigs available for this project, if your whole PC is 16 gigs, you may need to lower the buffer size to something a little bit smaller, even with int. If I set this to a float value to hold this big long decimal, then that 16 gigs turns into a little over 130 gigs of RAM. Same data, same level of specificity, but now because we have normalized it and turned it into this float value, we need a machine that can store a 130 gig buffer. And I'm assuming most of you don't have 130 gigs of memory on your machine. I don't. This was actually a problem of some that was causing me some trouble early on, because I was kicking off training and I would come back 30 minutes later and my my desktop had frozen up. I could no longer use my computer, and I couldn't figure out why. So I finally ran it and then started printing out memory values and saw the buffer at 130 gigs and realized that that's what was going on, that I had used the wrong data type. I had used a float, and I was storing a big long float value. So what we're actually going to do, we're going to store everything as int, and then when it comes time to use those values, we are going to normalize them on their way into the network. It's not as clean process-wise. You know, in a perfect world, I would like to be able to store values in a buffer and read them out from the network exactly as they're stored and just have it accept things as they are in the real world. But that is not actually practical with the way we're set up here. So we're going to go ahead and copy that. So this is going to be next state memory. Okay. And then we're going to do action memory. So self.action memory is equal to np dot zeros, and this will just be self.memsize okay, and this one can also be dtype np dot uint8. And reward memory. Actually, this one, we're going to do float 32 on these. Those won't have the same impact. You can play around with making those uint8 as well. In my original version of the code, they are floats, so I'm not going to deviate from that for now. They probably work fine as uint, but we're going to stick to the one that I know works. All right, we're going to do self.reward memory equals also np dot zeros self.memsize and dtype equals np.float 32 and self.terminal memory is going to be np.zeros and self.memsize, and dtype here is actually going to be bool. And self.device is equal to device. Okay, that's our init method. We're going to define a can sample method that's basically just, hey, do we have enough to sample? So I'm going to say def can sample self batch size. This is something that you definitely want to play with based on use case. So we're going to say, let me type and then I'll explain it. So if self.memCounter is greater, then we'll say self. Oh, you know what? I also messed something up above, and it's going to equal. Okay. did not do what I wanted it to. All right, so if this is greater than batch size by 5, then return true, else return false. Okay, so what we're trying to do here is we're trying to make sure that we're not just training on, you know, a very small batch count. So if you only have, you know, if you have less than a batch in the buffer, you don't even have enough values to return, so we always want that to be false. But then even if your batch size is 64 and you only have 64 values, well, you don't want it to rapidly pull in the same 64 values over and over again and start training on them. You're going to end up with a skewed, a very skewed network very quickly. Right now, I'm playing with this as, you know, batch size times 5 because, you know, we're starting from scratch on the network. If you wanted to be able to, say, kick off training and stop it at some point and pick it back up later, you actually want to increase this number. So you might want it to have 100 times batch size. You might want it to just run for 60,000 iterations without attempting to train, just so you have a good base of information to start with. Starting out with this as a very low number on a trained network is a really good way to turn a trained network into a no longer trained network. So just keep that in mind. This is perfect for starting from scratch. That is a value, though, that you want to tweak if you, you know, start working with other, if you needed to pick up training halfway through. All right, so we're going to do store transition, and that's going to take self, state, action, reward, next state, and done. And here we're going to set our target index. So again, we're not appending, we are keeping track of where our index is, and then we're, you know, filling up to that index. When the index gets to the end, it's going to loop back around and start at the beginning. So we're going to say index equals self.mem ctr %self.mem size, and that's the looping part. So basically, whatever your mem counter is, you know, if the mem counter is suddenly, if our total max size, our mem size is 500,000, and our mem counter is 500,001, it's going to loop back around and index will now equal 1. So self.state memory, we'll say index will be equal to state, and we're going to just paste that a few times because we're going to be reusing parts of it. Okay, so here this is going to, actually it's still going to be index. I deleted the wrong part. We're going to say, instead of state memory, this will be next state memory will be equal to, not where I wanted to go. All right, next state memory will be equal to next state. Here, we're going to say action memory And this one's going to be a little bit different. So action memory index is going to be torch.tensor action .detach .cpu. And this is the this is what's actually coming out of our model. That's why that one's a little bit different. All right, and then we're going to do reward memory. And that'll just be reward, not return, reward. And then we're going to do terminal memory will be equal to done. And then finally, we're just going to say self.memctr plus equals 1. Okay, that's our store transition method. Now our final method in buffer is going to be def sample buffer. And this is going to take self and batch size. Okay, and here we're going to go ahead and say maxmem is equal to the minimum of self.memCounter and self.memSize. So basically we want to know how much actual data is in the buffer. We know that memSize is going to be, the total, that memCounter will start out very small, but will eventually be well off into the millions. And we know that memSize is the total amount of memory that could be in the buffer. So if memCounter is less than memSize, then that's how much memory is available. If memCounter is greater than memSize, then memSize is going to be the amount of data available. So we're going to say batch equals np.random.choice, and we're going to pass in maxmem, and let's see. Oh, hang on. All right, we're going to pass in maxmem and batch size. And we're going to say states is equal to self.stateMemory batch. So this is basically going to return a set of indices, and this is going to select those indices. So we're going to say next states is equal to self.nextStateMemory batch. We will say that actions equal to self.actionMemory batch. We'll say rewards. Nope, not resource warning. Rewards is equal to self.rewardMemory batch. And dones is equal to self.terminalMemory batch. All right, and then we need to convert all of these to PyTorch tensors. So this is going to be states equals torch.tensor states dtype equals torch.float32. .2 self.device. And then really, this is probably where we can do some copy paste just a little bit here. Okay, so this is now going to be next states. Okay, and then this is going to be actions. And actions is going to be equal to actions. And you can keep your data types here. That's going to stay the same. And rewards. Okay. And dones. And this is the only one that we're going to change. So we're going to say dones, and then this is going to be torch.bool. Okay. And then we will return states, actions, rewards, next states, and dones. All right, and at that point, we have our complete replay buffer. I'm going to go ahead and end the video here. In the next video, we're going to go ahead and start working on the agent and the train method. So I'll see you there. Welcome to part 11 of Zombies and Reinforcement Learning. Today, we are going to build the model. So let's go ahead and we are going to create a model.py. And the first thing we're going to do in our model.py is get a few of our imports in. So we're going to import torch. We're going to import torch.nn as nn. And we're going to import torch.nn.functional as f. All right. And let's talk a little bit about our structure here. So we're going to create a zombie net. It's going to have 4 CNN layers, so 4 convolutional neural networks, because the observations in this case are image observations. Obviously, if you had some other numerical observation type, you might not need that. So we're going to have 4 CNNs, and then we are going to have 3 FC layers, fully connected layers. So 3 of sort of your standard linear layers. And then our output is going to be, let's see, what did I make the output? All right, our output is going to be action dimensions. So output equals action dim. All right, and what that's going to end up being is something that looks like this. So it'll output something to this effect, and then we'll basically pull this out and say, hey, this was a 2, or an action 2. All right, let's go ahead and get started. So we're going to say class zombienet, inheriting from nn.module. And we're going to go ahead and define our init method. So def init, and that auto-completed more than I wanted it to. So we're going to take in action dims. Hidden dim is going to be, I believe we're going to end up with 1024. So let's go ahead and make that our default. Also, that's doesn't need to be a plus. Okay. We'll default dropout to 0. And observation shape will be none. Okay. Here we're going to call super with self, and actually zombienet and self, and self. Okay. So let's go ahead and define our convolutional neural networks here. Self.conv1 is equal to nn.conv2d, and we're going to say in channels will be 1, out channels will be 2, or sorry, out channels will be 8. Kernel size is 4, and stride is 2. And I kind of mentioned it in the last video. I'm going through this section with the assumption that you kind of already know how to work with neural networks. If that's not the case, you should definitely go and take a course on convolutional nets and neural networks in general. I can put some recommendations down in the video descriptions. There's some great stuff out there, but this is not intended to be that. This series is focused on the environment creation and environment conversion. So I'm not going to try to go into depth here, and there are better people to cover it anyway. All right, we're just going to copy that a few times. So this is going to become conv2, and 3, and 4. Okay. And then instead of in channels 1 here, we're going to say 8. So you always want to line up your in channels of the next network with your out channels of the previous network, because these are going to flow in, and you generally kind of stair step them up. So what a convolutional net is doing effectively is it's going to take, your image data, it's going to slowly collapse that down into actual data among X number of channels. It's going to try to extract features from the image. And if you're wondering how I picked this particular number of layers, a lot of it was experimentation. This is what ended up working for the problem. Okay, and we're going to make, as we get smaller, we're going to make our kernel size smaller, and we're going to keep stride as 2. All right, and then in channels here is going to be 32, and out channels is going to be 64. And our kernel size again will be 3. Okay, we're going to implement pooling. Is equal to nn.maxPool 2D. Okay. Kernel size equals 2, and stride equals 2. Okay. I decided instead of, and this is just useful if you end up playing with various channel sizes and numbers, we're going to define a function to calculate the convolutional output. So let's go ahead and do def, and we'll come back up at the init method in a minute. We're not done. Calculate conv, I did that plus again, conv output, and self and observation shape. Okay. And we're going to say x equals torch dot zeros, and we'll say 1, and star observation shape. And then we'll do x, and this will mimic what we're doing in the forward pass, equals self.pool, f.relu, self.conv1, x, okay, and then we will do x equals self.relu, self.conv2, x, and then really this next one will look a lot like the one up above it, except this will be conv3, and we're going to copy that one. Z. And this will become conv4. Okay. And then finally, we're going to say return x.view. This will reshape it. -1. Dot shape at 0. All right, so let me just look at this and make sure I got it right. Yep, torch.zeros, conv1, conv2, conv, oh, I did self.relu, and that should be f.relu. There is no self.relu. All right, that now looks correct. Conv2, conv3, conv4. So what this is going to do is this is going to calculate the output size coming out of this. So it's not 64, it's not a number that we've set. It's based on the size of the image coming in and the size of the image coming out after processing. So this is not, and there is a way to figure it out mathematically. Personally, I find just having a function in here that runs it through once and determines the size to be a lot easier for me. So I'm going to go ahead and say back in the init method, we're going to say conv output size equals self.calculate conv output, and we're going to feed in observation underscore shape. Okay. And then let's go ahead and print it out. This is a good output size. Okay. This will only happen once in the init method, so it's not like it's going to spam your output. Now we can go ahead and set up our, let's add some comments and make this a little cleaner. Okay. Okay, so we've got our convolutional layers and our fully connected layers. Let's go ahead and say self.fc1 equals nn.linear. And this is going to be conv output size, hidden dim. And normally this would be a number, you know, some thousand something random number coming out of this process. Not random, but you know what I mean. So, and we just get to plug in a variable. Self.fc2 equals nn.linear. And this is going to be hidden dim, hidden dim. We're going to copy and paste that one. And self.fc3 will become just the exact same thing as fc2. And then we're going to do self.output. And let me see if I'm even using fc3. I am using fc3. All right. Wanted to make sure we weren't adding that needlessly. All right, self.output will be nn.linear. And that will be your hidden dim and your action dim. And I realize up here I put dims. Let's just clean that up and make it dim to match the tense of the rest of these. All right, and then we will do self.dropout equals dropout. That's just going to be a value. And self.apply, and we'll be defining this in a moment, self.weights init. All right, let's go define our weights init as soon as I find it. All right, let's just go ahead and put it right under here. So we're going to define weights init, and what this helps us do. So out of the box, you know, you're going to get a bunch of random weights in a network. When you create just a blank neural net, random weights, initializing the weights a little bit more purposefully can help make sure that you don't have any weird outliers in the beginning that throw training off. So not always important. In this case, it did help stabilize things a little bit and help training. So we're going to say is instance m of nn.conv2d. Okay. So if it's a convolutional network, we want to use nn.init.chiming normal on m.weight. And we want to define our nonlinearity as ReLU. And then if m.bias is not none, then we want to say nn.init.constant. And m.bias and 0. Okay. Now we're going to fall back here and do elif. Nope, over too far. Okay. So elif we'll do is instance just like we did before. M of nn.linear. Okay. And I see it's erroring because I did elify. That is not what I intended there. Then nn.init.xavier. We're not going to do uniform, we're going to do normal. M, make sure you get that underscore at the end. M of nn.linear. Okay. Let's see. And I should not have put that colon there. Okay. If m.bias is not none, then we're going to do nn.init.constant m.bias 0. Okay. So this function should basically get all of the weights to Pygame normal for conv2d and Xavier normal for all of the linear layers. Okay. So finally, let's go ahead and start to add our forward method, the meat of this model actually doing something. So we're going to say def forward. And it's going to take self and x as parameters. And then this is where, so if you remember back in when we were setting up the game, I mentioned that we would need to store, normalized values. So values between 0 and 1 for images, but that we couldn't store them right off the bat because we were going to need to, because that would make a giant input buffer. So our observation is returning something that's going to have, numbers between 1 and 255 in it. So now over here in the model, the first step of our forward method needs to be x equals x divided by 255. So we're just going to go ahead and normalize those images on the first layer. Now we can do, really, we can come up here because this is going to be very similar. So we can copy and paste. And we don't need this one, so we can get rid of that. But everything else basically can stay. That's all right. And then we can do our x equals x.view, x.size 0, and -1. Okay, and then we can do our fully connected layers. So we're going to do x equals f.value, and we'll do self.fc1 and x. And then we're going to actually make a dropout optional. So we're going to say if self.dropout is greater than 0, then we want to go ahead and call x equals f.dropout. So we're using torch functional. xp equals self.dropout. That's dropout percentage. Okay. And then I'm going to go ahead and okay, that didn't get quite what I wanted. All right, so we're just going to go ahead and copy that. And I am going to come down here and we're going to put another in between we're going to go ahead and do x equals f.ReLU. And this is going to be self.fc2 of x. Okay. And then finally down here, we are going to have x equals f.ReLU, self.fc3 x, and then we'll do output equals self.output x, and you don't usually want dropout between your final layer and your output layer. That tends to make performance worse. And we want to return output. Okay. Now we need just some helper functions here, both inside and outside the model, or outside the class. So we're going to define save the model, and we're going to say self, and we're going to say file name. We'll be feeding in one later, but we want to go ahead and give it a default. So this will be models/latest.pt. Okay. So we're going to do a try. Actually, no. For save the model, we're not going to do our try. We're going to do a try on load. So for save the model, we're going to do torch.save and self.stateDict and file name. Okay, and then we'll also do def load model. And for load the model, we'll take the same params. We're going to say self and file name equals models/latest.pt. Okay, and then here we'll do a try for self.load_stateDict torch.load file name. And print. So if this worked, we're going to go ahead and say printf loaded weights from file name. Okay. And accept. And the only thing we're going to catch here is a file not found error. So we're going to say accept file not found error. We kind of want anything else to just go ahead and crash. We're going to say print f no weights file found at file name. Okay, so there's our load the model successfully. And then we're going to define two other functions that are outside of the model itself. And we could stick these anywhere, but this is just the most logical place for me to put them. So we're going to say def soft updates, target source, and a tau. So in DQN, we're actually going to have two value networks, and then each value network will have a target network. And that target network is intended to lag behind the primary network, and it provides a certain degree of stability by lagging behind. So the soft update and hard update functions, soft update is basically intended to allow us to soft update that target and keep it close to the main network without quite having the same swings as the main network. So we're going to say tau equals 0.005. That's our update amount. And then we're going to say for target param. Now, if I could type, param in zip target.parameters. Oh, I misspelled target as well. Okay. Okay, so for target.parameters and source.parameters. And we're going to do target param data.copy. And it's not autofilling here because it doesn't know what these params are. Target param data times, let's see, and we're going to do 1.0 minus tau. So basically what we're doing, well here, let me finish typing it and then I'll explain it a little bit better. So plus param.data times tau. All right, so let's think about what's happening here. So in our soft update, we are basically saying you've got a target param and a param, so the source model. So in the target model, we're saying that we're going to multiply the target param by 1.0 minus tau. So tau is very, very small. So this is going to be, let's say our target param. So let's say target is 5, and they wouldn't really be nice round numbers like this, but let's assume they are. So, and then let's say that source equals, we'll do 7. We'll say source is 7. So let's go ahead and pull up our calculator. And we're going to say that, so target param, so 1.0 minus 0.005 is really close to 1. So we're going to multiply that by our target, which is 5. All right, so what we end up with is a number that's super close to 5. So that is 4.975 would be the value of the left side here. And then our 7, our source, which is what's coming from param.data, times tau, 0.005, so our very small number. So that ends up being 0.35. And if we add that, so 0.035 to 4.975, we end up with 5.01. So what's the point here? What are we doing? So what this does is it very, very, very incrementally edges the target towards the source. So in this case, our target was 5, our source was 7, and it is incrementally moving 5 towards 7 by 0.01 in this case, based on the value of tau. Obviously, if tau was larger, then we would move towards that value more quickly. We actually don't want it to. We want it to intentionally lag behind a little bit. So, all right. We can get rid of that. That was just for demonstration purposes. We are also going to do a hard update. So just copy that, paste it, And then we're going to change the word soft to hard. And we no longer need tau because this is just going to be a direct copy. And in this case, instead of copying this whole thing, we just need that. All right. Now the last thing we're going to do before we exit the video here is we're going to go ahead and test and just make sure that our model actually returns something, or at least can be created. I think can be created is our target here. So let me go and take a look at our agent code. We're going to go ahead and create an agent.py. And we won't be using very much in here right now. I just want to go ahead and from model, import ZombieNet hard update, soft update. And we're going to go ahead and say model, we'll delete this part later, but I just want to go ahead and test it. So model equals ZombieNet. And we will say that action dim is 1, and hidden dim is 1, and hidden layer, let's see, dropout is 0.1, and observation shape is 4. I'm making all of these numbers up. I just want to make sure that it actually creates and doesn't give us any errors. And we're just going to run agent.py, and it says cannot import hard update from model. Okay. Let's go see what we messed up. It may just be that I didn't save the file. All right, I'm going to resave and rerun. All right, must be an iterable, not an int. Okay, that's fine. It's expecting something like this, I believe. We'll play with this for a minute until we get it right. Nope. Let's see. Do you need a list? Yeah, I think it does. I think it needs... Okay, so it didn't like input size 1.4, expected unbatched, let's see. I think right now what we're dealing with is just that my test data here is not really mimicking the live data very well. Hang on, let me play with this for a moment. All right, so I found the issue. We needed to pass in parentheses 12828. That is going to mimic the batch size and then the image size that we're passing in. And we are getting an error. So let's go take a look and see what that error is. This is why we test. So let's see, model, yep, fan out. So it's saying linear object has no attribute dim. And that is happening on line 43 in weights init. So let's go take a look at 43. So Xavier normal mm of nn dot linear, and let me take a look at my working code and we'll see what's going on here. Okay, so it seems like it's not liking, okay, elif is instance, nn.init.saviornormal. I see what's going on. It just wanted m.wait here. That was my fault. Okay. Okay, let's save and go run it again. All right, and you'll notice that we got our convolutional output size of 64. And the cool thing about doing this dynamically is it means you can play with various variables and see what they would do to your output size. So like if I come in here, and obviously you can do that anyway, it just takes more math to do it without. So if I come in here and I make this 32 and rerun it, now we have an output size of 32 instead of 64. Not normally quite the linear mapping that we just saw there, but you get the idea. All right, well, so at this point we have our model. It's working, at least to the point of being able to create it and not throw errors. And that seems like a good place to end the video. In the next video, we're going to go ahead and build out this agent class so that we can start to move towards training our model. So I will see you in the next video. Welcome to part 12 of Zombies and Reinforcement Learning. In this video, we're going to go ahead and start coding out the agent. So let's get right to it. All right, so we've already created an agent, agent.py. We're actually going to delete this line that we created in the last video because it is not necessary. And we're going to go ahead and do some more of our imports. So we're going to say from buffer, import replay buffer. This is really the class where it all kind of comes together. We're going to import torch, not token, torch. We're going to import torch.optim as optim. We are going to import torch.nn.functional as f. We will import date time. We will import time. From torch.utils.tensorboard, import summary writer. We're going to be using tensorboard to manage our logging. We'll need random. We will need OS. Okay. So our class name here is going to be agent. So just go down a couple lines and then do class agent. Okay. And then we're going to say def init. And we won't just need self here. We will also need env, dropout, hidden layer, learning rate, step repeat. That's going to be how many times in our environment it runs a given action, and gamma. All right. So in here, we're going to need to go ahead and say self.env equals env. We'll assume that we're passing in an environment. Self.step repeat equals step repeat. Self.gamma equals gamma. We will go ahead and get an observation and info. So observation info from self.env.reset. And then we'll go ahead and see if we have CUDA available. So self.device is equal to CUDA 0 if torch.cuda.is available, else CPU. And this is basically just checking to see, do you have a GPU, loaded? And then we're going to just give ourselves some output here. Model loaded on self.device. Okay. So we want to, and that's really because if this thing starts up on CPU, I don't necessarily want it to crash, but I really want to get some information on that. I want to find out, are we running on CPU? Because it's going to be really, really slow if we are. All right. We're going to say self.memory equals replay buffer. Max size equals 500,000. Now a word on this one. So this is expecting to be able to build a replay buffer of 16 gigs. If you have less than 16 gigs of memory on your computer, or maybe you're just, you have 16 gigs, but you need something to actually run your operating system, you may want to reduce this. Now, 500,000 is what I tested it with. It's what it works with. There's nothing saying you can't get by with a smaller replay buffer. That's something that you need to play with based on your own system memory constraints. So that is what I'm recommending, but if you need to drop that down, if you've only got 8 gigs, make it 250,000. If you've got a little bit more, up it. All right, we're going to do input shape is going to be observation dot shape. We will make n actions equal to env dot action space dot n, and device equals self dot device. And give me just a moment. I want to see if we actually defined an action space in the environment. And I don't think we did, so we need to. So let's come back over here to game. And up here in the init method, we are just going to go ahead and say self.action space is equal to gym dot spaces dot discrete 7, and we may need to import gym up here. So we're going to say import gymnasium as gym. Okay, and now over here, hopefully that will like us a little bit more. Okay, so that successfully defines memory. Now we're going to do self.model1 is equal to zombienet, and action dim equals env.action space, and we can actually tell it what env is so that we get our autocomplete. So if you come up here and put this down as zombienet, now we should start getting, we're still not getting action space. Just save all. It may just not want to not be ready to reread it. That's okay. So we'll go ahead and say action space .n hidden dim is going to be equal to hidden layer. Dropout is going to be equal to dropout. Oh, and you know what? There's my mistake. I said env equals zombienet. What I should have done is env equals, see, we don't even have it imported. That's why. From game import, what do we call it? We called it zombie shooter. Not strictly necessary to make the code run, but again, it's going to get us, it'll help it understand what the env is. All right, back down here. So we got as far as dropout. We need to do observation shape equals observation dot shape. And then we're going to take the whole thing and say to self.device. Okay. And then just copy and paste that. And you know what? It really helps if you put an equals there and there. And this is going to become self.model2. All right. All right, so we need to go ahead and create our target models. So really this can just be another copy. There's nothing special about the target models. So we're just gonna paste. And we're just going to relabel these target model 1. And target model 2. And then we can go ahead and say self.targetModel1 Actually, this is where we can use our hard update. And we can say self.targetModel1. And our source is going to be self.model1. And then just copy and paste that. And we will do the same thing for target model 2 and self.model2. Okay, we have successfully created our models and our target models. Now we can go ahead and say self.optimizer 1, because each model gets its own optimizer. We're going to say optim.atom and self.model1.parameters. And then we'll say LR, so the learning rate equals learning rate, and self.optimizer2 is equal to optim.atom as well. I could have copied, I suppose. Model2.parameters. And then LR equals learning rate. And we're using 2 here because we're going to take the min value between them, and that's going to help protect us from over allocation. Or sorry, overconfidence, not over allocation. Self.learning rate. Let's go ahead and do this. Equals learning rate, just to have it available. And then we're actually going to pull in one more import. This should help you figure out, sizing. So from Pympler, if I'm pronouncing that right, we're going to import a size of. And here, we're actually going to make the model spit out the size of memory, or the agent spit out the size of memory. So we're going to say print f, and we're going to say memory size, and then a size of, and dot a size of self dot memory. And then we'll do a little bit of calculation here. So we're going to say divided by, and we could just punch a number in here, but it's easier for me to see it in as the multiples. So 1024. Okay, times 1024. And what we're basically trying to do is break this down into from, I believe the default output is bytes to gigabytes. So that's going to give us the total size of our replay buffer that was just implemented in gigs. So, okay, so when you fire this up, when you create your agent, you know, you're going to get some information on whether it loaded on your GPU, and then you're going to get some information on your memory size. It's worth noting that the memory will load on your standard system memory, your CPU memory. The model itself will load on your GPU. So your GPU does not have to have the same amount of memory as the buffer. You could implement it to where the buffer went straight to GPU memory. I don't recommend it unless you have a really big GPU or a very small buffer. All right, so now we can go ahead and start on our train method now that we've made it through init. All right, so we're going to, and there's going to be a bunch of params on this one. So we're going to say def train, and this is going to take self episodes, max episode steps, summary writer suffix, it's going to take batch size, epsilon decay, and min epsilon, because we're using an epsilon greedy action selection here. Okay, we'll go ahead and define, so the summary writer is something that we're using with TensorBoard. So that's going to help us print out what's happening as we go. So we're going to say summary writer name is equal to, and we're going to put it in runs. This will put it in the runs directory. That's not required. You can put it anywhere you want. I'm going to say datetime .now .strftime, and then this will be percent capital Y dash percent lowercase m dash percent D underscore percent H dash percent capital M dash percent capital S. And that should get us year, month, day, hours, minutes, seconds in the file name. And the reason we're doing this is so it doesn't just overwrite every time. It will automatically pick a new it'll automatically pick a new file name for us just based on the time. All right, and then we're going to say underscore, and we'll put in summary writer prefix or suffix. And the reason we're doing this is we want to go ahead and we want to have a default name, so a time, a number that gets incremented every single time. But we also want the ability for you to label each run. Now maybe, because you're following a video tutorial, you're only going to run this a couple of times. You'll run it, hopefully it'll work, and, you know, success. But that's not how these things usually work. So I mentioned at the beginning of the series that I started this back in October as kind of a joke Halloween project. And it took, you know, a couple of months of tweaking to get everything working, specifically on the model and training side. And that meant that every single time I wanted to change parameters, I needed to have a way to label it, to log it, to see which parameters did better, which ones did worse. And that summary writer suffix, that variable, is allowing us to track that, to label our runs a little bit more easily. All right, so we're going to say writer equals summary writer, and we will be passing in summary writer name. And then we'll go ahead and create the path if for the models, os.path.exists models, put it in quotes, then os.makeDirs models. Okay, we're going to set total steps equal to 0. And then we're going to say for episode in range episodes and we will say go ahead and start out with does false, and episode reward equals 0. State info equals self.env.reset, and that should get our initial state. We'll say episode steps will also start out equal to 0, and then we will go ahead and say we're going to go ahead and capture episode start time equals to time.time. And this is just to monitor speed. This was also really important starting out because initially the game ran really slowly, and that impacted how fast training could run. So we want the ability to see how long things are taking. All right, we will go ahead and say while not done, and episode steps is less than max episode steps. We're going to go ahead and do our epsilon greedy action selection. So we'll say if random.random, not randint, if random.random is less than epsilon, then action will equal self.env.actionspace.sample. Else, we're going to say q values 1. So we're going to call self.model1.forward state.unsqueeze on 0. So we need to do a little bit of reshaping on state because it's not a batch. .2. So we're going to go ahead and send state. Remember, we're pulling state from an environment, and then we need to send it to the model but the model is running on the GPU. So we need to go ahead and send state to device, and that's going to be self.device. And then we need to grab the 0th element. All right, and then go ahead and copy and paste that. And we're going to do qValues2. We'll call model2.forward. And then we're going to say the actual qValues are equal to the torch.min of qValues1 and qValues2. And again, what we're doing there is we're trying to reduce overestimation. We're trying to stop this thing from, accidentally having one model that really thinks an action's good and the other that doesn't think it's all that great. We're going to go with the one that doesn't think it's all that great. We want this to be a little bit more pessimistic about its selections. And then finally, we're going to say action equals torch.argmax, and we're going to say qValues and dim, lost our paren there, dim equals -1 dot item. So what this will do, again, our existing output is going to look something like, this, but with probabilities. This is going to convert that, type of distribution into, hey, this is action, 2 or 3 or, whatever the highlighted value is. That's what our torch.argmax is going to do. All right. We're going to go ahead and take a step in the environment. So next state, reward, done, truncated. Actually, we're not even using truncated or info, so let's just do underscores for those. Equals self.env.step. And we're going to feed in action equals action, and repeat equals self.step repeat. Okay, so now we have taken our step in our first step in our environment. We can go ahead and store that transition. So this is where we're putting away the memory for future training use. So we're saying self.memory.store transition, state, action, reward, next state, done. We'll go ahead now that we've stored it, we can say state equals next state. We can go ahead and add episode reward plus equals reward. We can add episode steps plus equals 1. We can do total steps plus equals 1. And then we get down to the batch training section. So we're going to say if self.memory.can sample batch size, then states, actions, rewards, next states, dones equals self.memory.sample buffer of batch size. All right, and then we are going to need to make some changes to those values. So we're going to say dones is equal to dones.unsqueeze. on dimension 1 dot float. And then we will get the Q models from both, or Q values from both models. So current Q values. Okay, so we're going to do Q values 1 is equal to self.model 1 states. Very easy to typo something in here, so be careful. Q values 2 is equal to self.model two states. We're going to say actions equals actions dot unsqueeze 1 dot long QSA B 1 is going to be equal to Q values 1 dot gather. Oh, helps if I spell gather correctly. 1 on actions. So what's this line doing? This one is actually taking, so we just got a batch of Q values back from these models, right? So this was a bunch of values of which directions have, or which actions have which values. We're grabbing a long version of actions, and then what this gather is doing is it's taking the actions and it's grabbing the predicted Q values for those actions. So what this QSAB1 is the Q state action, the batch, so the values of the batch of actions. And then just like everything else, we're going to go ahead and turn that into a 2 as well on Q values 2 dot gather. Okay, so next we're going to go ahead and select a fresh batch of actions. So we're going to say action selection using main models. Okay, so we're going to say next actions 1 is equal to torch.argmax, and we'll say self.model1 next states. And we'll say dim equals 1 and keep dim equals true. Copy and paste that. And next actions 2. And you have to change model to 2 as well. And then we will go ahead and get the Q value of next states using the target models. So we're going to say next Q values 1 is equal to self.targetModel1 next states, and that will be added a dot gather 1 and next actions 1. And just like before, we're going to copy and paste that, and that will also be added to number 2 here, and model 2 and next actions 2. All right. And then we're also going to take the minimum, just like we did in the real action selection. So take the minimum of the next Q values. Okay. So we're going to say next Q values is equal to torch.min next Q values 1 and next Q values 2. Okay. We will compute the target value. And that's going to be target B for target batch equals rewards dot unsqueeze 1. And unsqueeze is just adding an extra dimension, if I haven't mentioned that before. So that's going to be 1 minus done times self.gamma times next Q values. Okay, so let's talk for a moment about what's happening here. So we're looking for the value of the target batch. And we're doing that by saying, so we in the target batch is, your next state, the value of the next thing that you're doing. So the first thing we're taking is the reward. We know what the rewards are. So, maybe the reward is a 2. We know that, or a 1. We know that the current reward is a 1. We are then looking for what the next predicted value is. So that's next Q values. And we're multiplying it by gamma. And gamma is the discount factor. So the discount factor in this case is 0.99. So we're basically saying that future rewards, because they're not necessarily guaranteed, they're just predicted, we're saying future predicted rewards are still very highly valued, but they're valued a little bit less than current rewards. So your current reward is the real reward, whatever you're getting right now. Your future predicted reward is devalued by basically 1% based on what we're passing in. And let's talk about what 1 minus done means. So done is going to be a value of 0. So most of the time, if it's not done, it's 0. So if the episode is still going, if that wasn't the last step, then 1 minus done just turns into 1, and then it doesn't change the value of the equation. You're just multiplying 1 by self.gamma next Q values. If it is done, so done will come back as a 1, then 1 minus 1 ends up equaling 0. And then it basically cancels out the second half of this equation. So you will, if you're in your terminal state, if you're done, there's nothing else to do in the episode, then there obviously is no next Q value. There's no next value of an action because the episode's over. There's nothing else you can do. So that's what's going on there. So we're going to go ahead and calculate our loss. So loss 1 is equal to f dot smooth L1 loss on QSA B1 and target B, and we'll have to detach that. And we're just going to copy paste that. And we'll do loss 2 will be QSAB2. And then we'll go ahead and do, this is our TensorBoard section. We're going to do writer.add scalar. And this is going to be loss/model_1. And these should track pretty closely, but it is interesting information if they're not. So we do want to track loss for both of our models. So loss1.item. Oh, I did not mean to go there. And then we'll do total steps. And the reason we're doing total steps, and the whole reason we're tracking total steps is actually for TensorBoard, is we want to see a loss trend that covers across episodes. So we want to see loss over the entire course of training, not necessarily loss for a single game, a single play. So we can go ahead and copy and paste that. So we'll do loss model2, loss2.item. And then I had also wanted to add some comments here. Compute loss. Okay. So we've successfully computed our loss. We've got all our values. Now we need to go ahead and do backprop and optimization. Okay. So we'll do self.model1.0grad. Loss1.backward. And self.optimizer1.step. Not state, step. Okay. And then we're just going to copy and paste this. And I did not copy and paste the way I wanted it to. There we go. All right, we're going to do model 2 and loss 2 and optimizer 2. Okay. So we have successfully done our optimizer step. We've gotten our loss, and then we want to go ahead and do our soft update. So we're only going to do it so often. I'm going to say if episode steps %4 is equal to 0. Then we're going to do a soft update and self.targetModel1 and self.model1. And copy and paste that. And self.targetModel2 to self.model2. All right. Now we're going to come in a couple layers here. So we want to be out of the for loop, but still inside train. So that's going to put us, actually, hang on. We want to be inside for episode in range. We're going to be outside of while not done. All right. So this is perfect. This is where we want to be. So we're going to say self.model.model1, sorry, dot save the model. File name equals file name, or actually file name in this case, we don't have file name defined as a variable. So it's going to be model/dqn1.pt. Okay, copy and paste that. And we're going to say model2, dqn2. Simple enough. And then we'll do writer.add scalar score. So this is where we're actually going to track our score over time. So we'll do episode reward. And let's see. And episode. And we'll also do writer.add scalar epsilon. And you might wonder, why do we want to track epsilon? It's something that we're decaying at a predictable rate. Well, sometimes you can see some interesting, changes in performance as epsilon decays. And, you might see that that performance is going down as epsilon decays. And you could, think that your model is getting worse. When in reality, it's just that the model is slowly taking over from randomness. And then once epsilon decays all the way down, you'll start to see the actual model improvements. So we do want to track that because it can affect some of the other variables on the graph, and it makes it easier to make sense of the data. All right, so we'll say if epsilon less than min epsilon, we're going to say epsilon times equals epsilon decay. And episode, let's see, episode time is equal to time dot time, not time dot time, minus episode start time. And then we're just going to say, we're going to give ourselves some output here. We're going to say completed episode with score, let's see, episode reward. We'll do a print episode time, and we'll just format that to 1F seconds. And then we will go ahead and print episode steps. All right, and that takes us to the end of our agent class and the end of this video. We're not going to test it in this one. In the next video, we're going to go ahead and put together a train.py, which is going to tie it all together, call agent, kickoff training, and then hopefully you can start to see some results of the AI playing the game. So I will see you in the next video. Welcome to Zombies and Reinforcement Learning Part 13. In this video, we're going to go ahead and actually start building out the train.py. This is also where we're going to start to tie it all together. So we're probably going to run into all the places that we've messed something up, or I've put in a typo, or any of that fun stuff. So this is it. This is when we get to finally kick off the agent's training. So let's go ahead and create a train.py. And we'll also create a test.py. We'll need that a little bit later. Those two go together. And in train.py, we are going to go ahead and just get our imports in. So we're going to say from util import star. We're going to say from game import zombie shooter. From agent import agent, the agent we built previously. All right, we'll go ahead and we're going to set episodes. This is just going to be a whole bunch of parameters. So episodes will be equal to 10,000. Max episode steps will also be equal to 10,000. If you have any problems, you may want to lower this a little bit so that you can see, you might get some results that are, I don't want to say more consistent, but if your agent's getting stuck or something, maybe a lower value makes sense. I ended up increasing this as, you know, I built out the solution to just kind of let it play until the agent died each time. So we're going to go ahead and set total steps to 0 to start with. Step repeat. So how often do we want a new action to happen every time? We're going to set to 4. And then you don't have to do this, but something I did here is set max episode steps to max episode steps divided by step repeat. So basically, I wanted to be able to set the total number of game steps here, and then understanding that it's going to take 4 steps for every one that's input. So the actual max episode steps is 2,500 in this scenario. You could obviously just cut straight to it and make this number 2,500 and skip this. This helped me think about it in terms of actual steps taken divided by step repeat equals the target number of steps we're going to take. We're going to say batch size is equal to 64. Learning rate is going to be equal to 0.0001. Epsilon will start at 1. Min epsilon will be 0.1. Epsilon decay, and this is a number I found just by experimenting, but I landed on 0.995. You can play around with it. Gamma will be equal to 0.99. Hidden layer size will be 1024. And we're going to do a dropout of 0.2. All right, now to go ahead and create the environment. So we're going to set a couple window height and here, let's put window width first. Window width and window height are both going to be equal to 1200 and then 800. Okay. And world width. And oh, you know what? It's the syntax highlighting's off because I put a period there instead of a comma. That would do it. All right, so world width and world height will be equal to 1800 and 1200. So we're just making the world a little bigger than the window. And then we're going to go ahead and say FPS is equal to 60. This value should get overridden because of some of our other logic, but let's go ahead and use it. So zombie shooter, all right, window width equals window width. Okay, and window height is equal to window height. And let's just go down to the next line. We'll say world height equals world height, and world width equals world width. And you could have just coded these in to the agent, or to the game. I would prefer not to. I prefer to keep these things external. If you wanted to play with them, you know, change some of the variables, see how it reacts to different, different parameters, different world sizes, all that good stuff. All right, so sound equals false, and then I don't think we need anything else. I think that's all we put in. All right, we are going to go ahead and put together our summary writer suffix, and this is something that you should really just play with based on your needs. These are all the variables that I ended up working with as I built this out. So I called it DQN LR equals learning rate, and then underscore HL equals hidden layer. And you can kind of start to see how I'm using this. And then batch size equals batch size. And we'll go ahead and throw in a dropout, what our dropout is. And again, there is no technical requirement here. This is just what's going to show up as the label for this training run after the date. So the reason we're putting this in is that you might want to experiment with different parameters. Like let's say you wanted to see how it worked with a hidden layer of 756 or 512. Well, you need something in that training run name to show you what parameters you ran it with. Or you need to do it in some other way. Print it out into a file, show it. You need some way to show what your params were as you were experimenting, because these things can take days to train. This agent, and we'll talk about that a little bit more later, but this agent could take 30, 40 hours to train. So if you're running experiments over the course of a week, or realistically, sometimes a couple of months, you need some kind of labeling that's going to tell you what those experiments were. All right, let's go ahead, and I'm just going to run this and see if we should at least get an environment. Yep, and it goes away. All right, that's what we're looking for. I would not have expected it to pop up though. Let's see. Let me see if I missed something in game. Oh, you know what? We do need to, let's go take a look at our game.py. Oh, that is game.py. Okay. So we've got human equals false is the default, and we've only, okay, I see what we missed here. So we're setting, if you pass in human, we are setting sound to false, which is, or sound to false if you say human equals false. But we're not doing anything else. So something we need to do here is we need to set os.environ. And I guess we need to come up here and import os. And we're doing this because we don't want it to actually display anything. We want it to, basically just run in the background. So the fact that we got a pop-up there, and just in case you missed it, let me show you what I mean. Okay. So if we come over here and run train again, that pop-up, the window that came up, we don't actually want the game to pop up on the screen. If human equals false, do not display game. That's really what we're looking for. And in fact, in my original code base, it looks like I used render mode for this. So let's go ahead and actually fix it to do the same. So let's go back over to game, and we're going to play with this a little bit. Instead of human equals false, we are going to say render mode, and we're going to default it to human. And I'm using render mode because that's a little bit of more of a standard param for Gym. You'll see render mode in other places. So I'm just going to say, let's see, we'll get rid of that. And we are still going to use self.human down in the environment. I'm not going to take that variable away completely. What I'm going to do is say if render mode equals human, then we're going to say self.sound equals sound and self.human equals true. Okay. Else, if you pass in anything else, or we'll just say elif render mode is equal to RGB. So we'll say self.sound equals false, self.human equals false, and we'll go ahead and say os.environ, and here we're going to say SDL underscore video driver equals dummy. And this is just a Pygame thing that should basically turn off the video rendering. All right, that looks good. Let's do one more thing. Let's go ahead, again, just thinking about future environment use. Let's just go ahead and say else raise exception invalid video drive or invalid render mode. So what this should do is we should be able to pass in human or RGB or nothing, and if we pass in nothing or if we pass in something invalid, it should give us, so let's go ahead and do render mode equals stuff. Let's just go ahead and test that scenario out. All right, cool. So we got our invalid render mode. So now we should be able to see RGB. And let me just run it. Oh, we're still getting our pop-up. Why are we getting our pop-up? Let's see. This is definitely something we need to fix. Ah, I see the problem. Okay. So we're setting render mode down here and the SQL driver environment down here, but we're setting our Pygame init and mode and caption and all that way up here. So what we're going to do is I'm just going to cut these 9 lines here, and we're going to come up and put them right above Pygame init. So by the time we get down here, we should already have them set. Okay. All right, cool. So that time we did not get our pop-up, which is exactly what we expected. All right, let's go on with our training, with our train.py here. So this is going to be agent. We're going to declare our agent equals agent. We need to pass in an env. We're going to pass in our dropout equals dropout. Our hidden layer equals hidden layer. We'll go down to the next line here. Learning rate equals learning rate. Step repeat equals step repeat. And gamma equals gamma. Okay. And then finally, we're going to call agent.train. We already have our train method. Episodes equals episodes equals, let's see, what did we call it? We did call it episodes. Max episode steps equals max episode steps. Summary writer suffix equals summary writer suffix. And in fact, actually, no, we'll leave that alone. Batch size equals batch size. In the original code base, I had appended stage 1 or phase 1 because there were multiple phases, but then that ended up not being very useful. So epsilon equals epsilon. Epsilon decay equals epsilon decay. And then min epsilon equals min epsilon. All right. Moment of truth. It's probably going to crash. I'm sure there's a typo somewhere. Okay, so no crash, but lots and lots of output. And that is, oh, and then it died. Okay. Okay, let's go see why. So if I go look at game.py here, actually no, it's going to be agent.py, and let's take a look at the train method. So we did 4 episode in range episodes. So we got lots of, we got prints in here somewhere. So for context, this should have kicked off a training run that should take, 30 hours. It should not have returned in a few minutes. And that's what I'm confused about here. Okay, 4 episode in range episodes. That all looks fine. Done equals false. While not done and episode steps. Yep, that while loop looks good. I don't think we're doing any returns. Here, let's just look for the word return. Reward done, if memory. Yep, all that looks good. Epsilon, episode time. All right, well, let's go ahead and fix our print because that's probably going to be easier to figure out. Oh, I wonder. Print. Okay. What's the... Okay, so we're basically going to say if self.human. Actually, you know what? I don't even think we need these. I don't think they're useful in the console logs. So we'll get rid of that. We will comment that out. We'll comment that out. Very useful when you're developing, but not now that we've basically got an environment set up. All right, let's try it again. I don't expect it to run longer. Okay, we're still getting that bullet launched. But where? Ah, bullet.py. Okay. Okay. We're saving bullet.py, and let's run it again. You'll notice here that we've got our memory printout of 15.26 gigs. That is what you should expect to see. But then we're not getting anything else. We're returning and closing. And I have a feeling it has something to do with game.py, like maybe we're closing Pygame. I'm going to pause the video for a moment and take a look at it and come back when I see what's wrong. All right, so I think I've found it, or at least a possible cause here, something we need to change. So in game.py, under game over, right here we've got Pygame time wait, and then Pygame.quit and sys.exit. So what we need to do here is we just need to say, oh, let me find that again, game over. So instead of having these here, we can either remove them, or what I'll probably do is if self.human, then we want to do a wait. And we will go ahead and get rid of Pygame.quit. I'm just going to comment that out because there's no real reason we want to quit Pygame. We just want to keep it running. All right, so let's try train.py again. Okay, and it's running and not failing, but it should be running faster. So let's take a look. I have a feeling I know what's going on here. Clock.tick. Okay, no, that should be fine. Okay, the first episode was 38 seconds. Not horrible, but I would have expected it to end sooner. So let's go ahead. We have our models being printed out. Let's go ahead and write our test.py. And that should help us see what might be going on here. You know, maybe why we're seeing the results we are. And we'll just let that run in the meantime. That's fine. So let's go take a look, test.py, and we're actually going to copy some of these params from train.py. In fact, let's just go ahead and yank the entire all right, let's go ahead and pull the entire train.py over as a starting point because we'll need a lot of it. We will still need a lot of the params. We'll need the game imports. We're not going to rely on a test method. We're just going to code the entire thing out in here. So we will need, let's see. We've got that. Max episode steps can be as many as we want. That's fine. Episodes is fine. Okay, that looks good. In this case, we actually want render mode to be human now. And then we're going to say, let's see, we're going to go ahead and load our models. So we don't want agent.train. We want model 1 will be equal to zombienet. Oh, we may need to actually do some imports too. Let's see. Yes. So back up here, we are going to go ahead and say from model import ZombieNet, and we'll grab other things as we need them. So, and then really we can get rid of summary writer. And okay. So ZombieNet action dim equals env.actionspace.n. Hidden layer or hidden dim will equal hidden layer. Observation shape will equal observation, and we don't have observation shape in here. Let's go set that or get that. Hang on. All right, we're going to say observation info equals env.reset. Okay. And now we can come down here and say observation shape equals observation.shape. Okay, and then we'll send both of these to device. And we need to go ahead and define device. So device is going to be CUDA 0 if torch, not Tabor. Let's see. We'll need to go ahead and import torch. Okay. So if torch.cuda.is available, else CPU. Okay. We can just paste model 1 to model 2. And then for both of these, remember we're not training now, we're testing. So we can say model 1 dot load the model, and file name equals models/dqn1.pt, and model 2 dot load the model, file name equals models/dqn2.pt. Set both models to eval, and model2.eval, and then we go ahead and get into our test loop. So we'll be setting, we've already got step repeat. We'll say for episode in range episodes. And while I'm thinking about it, let's go ahead and just set episodes to something reasonable. For testing, we probably just want 1. We probably don't want more, but I'm leaving the range in there in case you want to. Done is equal to false. Episode reward is equal to 0, starting out. State info is equal to env.reset. Episode steps. This should look very, very similar to our training loop. A little bit different, but similar. Let's see. Be 0. All right, and then we want our time. So I'm going to say episode start time is going to be equal to time.time. Helps if I have an equals and also if I actually import time. So let's go grab that one as well. Let's see. Okay. So we've got our episode start time is equal to time.time while not done and episode steps less than max episode steps. Then if random.random, we will need random here. Port random. And we actually do still want some randomness even in our trained model. So we're going to go ahead and say 0.05 as our epsilon, which means most of the time, 95% of the time, it should take an action based on the model, and the rest of the time it should still get some randomness in the environment. All right, so if random.random less than epsilon, then we want to go ahead and say action equals env.action space dot sample. Else model1 q values equals model1 dot forward state dot unsqueeze and on the 0th axis dot 2 device and the 0th element. And then we're basically just going to do the same thing with model 2. Okay. Q values is going to be equal to torch.min of model1 Q values and model2 Q values. And then action is going to be equal to torch.argmax. For Q values, dim is equal to -1 here, and keep dim true. Okay, and then we're going to go ahead and say next state, reward done truncated info equals env.step, action equals action. Repeat equals step repeat. State is equal to next state. And we're not actually, so in the regular training loop, you would store all of this in a buffer and then you would set state equals next state. We could just put state here instead of next state. I am keeping it this way just to have it look like the training loop a little bit more closely. All right. Let's see, plus equals reward and episode steps, let's see, plus equals 1. Okay, and then outside of our while loop, we're going to just go ahead and set episode time equal to time.time minus episode start time. Print. And then really this is going to look identical to the last 3 lines here. So let's come over here and I'm just gonna steal those. Okay, so let's run our test.py and see what's going on. Okay, so we've got some randomness. Right now, our agent clearly doesn't understand how to avoid zombies or what to do here. But what it does look like is that, you know, the agent's playing, it's able to interact with the environment in some way, and it's not just, you know, completely random, even though it's not playing, you know, well at this point. So this is, and it made it to level 2. That's not awful. All right, so at this point, we're in a place where we basically just need to let it train for a while, let it cook. You can see we're getting wildly divergent scores here. We're getting everything from -10 to -2 to, you know, 4 and 5. Something that's probably worth thinking about here is that -10, and by the way, it just finished with a score of 11. That's actually really good for how long it's been training. -10 here is actually not that bad. And the reason I'm saying that, so if the agent just sat there, if it did nothing at all, it would get a -5. Because it wouldn't have, you know, it would not have picked up health. It wouldn't have, it would have just sat there and waited for the zombies to come, and then that would have gotten, you know, -5 lives taken, and then have it fall over. A -10 implies that it actually stayed alive a little while, collected some health, took some hits, you know, etc. So, and then what's interesting here is it's not ending. We're not getting a done signal. Now that might be a bug. That might be something that we need to look at. So next state reward done truncated info. Yeah, because it threw the "you died" and then the agent's continuing to leave. So or run around, you know, move a little bit. So that might be why we're taking 40 seconds and getting larger negative values. All right, let's dig into that. So if we go over to game.py, I'm going to go look at my original code base and see what we're doing with the done variable. Okay, so if done break, that's fine. Reward done truncated is coming from self.step. Let's go. Okay, so we're in reset. We're setting self.done to false. That's fine. And then what we should be saying, yep, if self.level greater than 3, then self.done is 2. So basically, if you succeed, you're done. But we should also be setting this in game over. So let's see if we are, because we probably aren't. Okay, that's reset. Where was game over? Yep, and that is accurate. Nowhere in here are we setting self.done. All right, so let's just come up here and say self.done is equal to true. And this is why testing is important. If you're not able to see what's going on, you know, in the middle of training, you might miss that something like that, something just nothing to do with RL, just very obvious in the environment, is causing problems. So we've saved this. Let's go run our test.py and see if it successfully goes away once it finishes. it would be helpful in this phase if it was doing worse. All right, good. Our character's trapped. The zombies are coming. We just need her to hit a health of 0. All right. So it did successfully end in that case after 50 seconds. So what we're going to do, we're going to go ahead and Control-C this. I'm going to get rid of these 2 models. Yep, move to trash, that's fine. And then what we should see is we should actually see these episodes take a lot less time. Okay, 32 seconds versus, yep, and then that one ended in 4 seconds after 379 steps. All right, so we are successfully stopping at the end. So let's go ahead and look at some of our stats. If you're using VS Code and you have the TensorBoard plugin, you can hit Control-Shift-P, and we're going to launch TensorBoard. If you don't have the TensorBoard plugin, you can just go install it. Or if you're not using VS Code at all, you can always just launch TensorBoard separately pointed at your runs directory. So we're going to look at scalars here. And this is what I was talking about with being able to see the various runs. This is every time we run the code. I only want to see the latest because it's the only thing I care about right now. And what I'm interested in here is the score over time. You can also see, so the things we logged were loss, epsilon, and score. Some of these are self-explanatory. You obviously want score to go up over time. Loss can go up and down, and that's okay. You'll see, as the agent explores the environment a little bit more, you're going to see loss, change. But it could wobble. It could go up for a while. It should drop back down. The areas that I would be concerned about are if loss does nothing but go up, or if loss is nice and low, but despite loss being nice and low, the agent is not learning or not doing better. That would be something, I've seen scenarios where loss is super close to 0, but the agent is not actually doing anything useful. And then you will likely see a change in performance once epsilon decays. So like right now, we're getting scores of 5 and 7, and hey, looks great, right? But also epsilon is still 0.96 basically. So sure, the scores are great, but also the scores are going to be great because, or not great, but they're at least going to score occasionally because the agent's basically just doing random things. It's wandering around and shooting at things, randomly, and yeah, that's actually not a horrible strategy. Randomness will get you right about this for scores. So what you should expect to see is decent scores for a while it's mostly random. You'll actually see the scores tank once it gets down to a lower epsilon, and then they should slowly start to climb. If you don't have a PC that can run, has enough memory, or you don't have, either you don't have the memory, you don't have the GPU for it, or maybe you just, don't want to tie up your desktop for 20, 30 hours. I can recommend a service called Runpod. There are other things that do this. Just look for GPU hosting. Runpod is what I personally use in order to go and run this remotely. I have another video on how to set that up, and I will drop a link in the description. And I think this is probably a really good time to pause. I'm going to walk away and let this run for a while and just make sure that training continues. And then I will resume the video and we'll see how it did. So see you instantly for you and in a few hours for me. All right, I'm back, and let's take a look at how the agent is doing now. So you'll notice that we trained for about 800 iterations, and if you're still in sort of the default smoothing level, this just looks like noise. If you slide it all the way over here, though, you can see that what's really happening is it is slowly trending upwards over time, which is what we want to see. It's not going to learn really, really quickly, but we are moving in an upwards direction. So let's compare that to my original project. I'm actually going to pull that over. I screenshotted the performance at the time. So this was the first training run, and you'll notice that we got really, really slow training speeds, up to about 1,500 episodes. And then after that first, 1,500 episodes, it really started to take off, and then peaked after when we got to, somewhere over 3,500 was right around where it peaked. So that's kind of what you can expect here. I'm happy with seeing that it is training, it's learning. I'm not going to retrain the entire thing on the video because, again, it takes about 30 hours to do. And I really don't want to wait 30 hours to finish and post this video. I'm going to try to get it out today. So, but it's learning, it's training. You can expect within, however long 3,500 iterations takes for you. That's about what you're going to take to get to peak performance. But let's see how it's doing at the 800 mark. That's the cool thing about having a separate test.py, is we can test it as it goes. And you always want to look down here. The reason we have logging on loading weights from the weights file is to see if it actually loaded, and in this case it did. So it's not doing badly. It's wandering around. It has successfully shot a few zombies. It at least seems to have some understanding that it needs to stay away from them and that it needs to shoot at them, even though it's not doing either very well yet. All right, and we landed with a score of -3. Just for comparison, let's go take a look at the original and rerun the test.py. And this is a trained agent. It's still very spastic, but and you'll see this one is, wandering around and getting rid of zombies quite confidently. So this is where you can expect to get to, or at least where I got to. So what are your next steps? Well, a couple things you could do with this information. This whole course was on, our whole video series was on building a custom gym environment and what you could do with that custom gym environment. So things you could do next to really cement the knowledge in would be to create your own game and turn it into a gym environment, and then train an AI agent on it. That would be a really cool way to pick this up and run with it. You could take the current gym environment that we just built, and you could implement another algorithm to play it. Maybe for the discrete action space, so what I used here was Q learning. You could change it to a different action space and implement another algorithm. You could think of some way to take this and make it your own. this was a zombie game. Can you turn it into a space game or whatever you want to make it? And that to me is a really good way to take something like this where, hopefully you've learned something going through the walkthroughs, but you haven't had to take the knowledge and build something with it yet. So taking my code and doing something new with it is going to be a really good way to go from someone who's typed it all out and made it work and maybe done some troubleshooting to someone who really deeply understands it and can go and implement this from scratch on something else. A word on code reuse. You are more than welcome to use my code. You can repost it, you can talk about it. I would appreciate you attributing it back to me, should you choose to. In the video description, you will find a link to my Runpod video. If you want to train on Runpod, you'll also find a link to Discord. If you are interested in talking about these projects, and then I'll also link to a completed GitHub repo with all of the code. I would encourage you, if you've run into any bugs or issues, to spend as much time as you can just hacking away at it and getting it working yourself. But if you hit a wall that you can't get around, you are welcome to go and look at the GitHub. Or if you just want to download it and confirm it works, that is out there for your use. And then this is the end of the project. We've built it. I hope you've had a lot of fun. I had a lot of fun creating this and putting together the series. If you like what you're seeing and you are interested in watching more reinforcement learning content or robotics content or other sort of start to finish build videos, please hit subscribe. I will continue to post these things as long as I find them fun and interesting. So with that, I will say goodbye until the next project, and see you there.